Hello everyone, welcome to the first video in this new Python OOP series. In this series, we're going to properly learn object-oriented programming in Python. Now, in this very first video, we'll understand what classes, objects, and methods are. We will also go through what self actually means in Python object-oriented programming. Now, object-oriented programming is one of the most important concepts in Python because it helps us organize and structure code cleanly as applications grow larger. And in Python, many major libraries and frameworks use OOP extensively. So before moving on to more advanced concepts later in the series, we first need to build a base, a strong foundation. As software becomes more complex, managing code becomes increasingly difficult. OOP helps solve this problem by organizing logic into reusable and structured components. Frameworks like Django and FastAPI use OOP extensively. Machine learning libraries, too, like PyTorch, TensorFlow, also heavily rely on classes and objects internally. And large applications used in production-grade software use OOP because it improves readability, maintainability, and scalability. So what is OOP really? The easiest way to understand OOP is through the blueprint analogy. A class is like a blueprint. For example, a blueprint for a house defines its structure, its layout, and what it contains. The number of doors, the number of windows, the number of rooms. But the actual house built from that blueprint is the object. So, a class defines the structure and an object is the real instance created from it. Now let's move on to the Python code and build our first class. Now, we shall be implementing the simplest possible Python class. So we go class, user, and we go pass. The class keyword basically tells Python that we are defining a new custom type. User is simply the name of our class, and pass is a placeholder because the class is currently empty. At this point, user becomes a new data type created by us. Just like Python has built-in types such as integer and string, we can also create our own custom types. Now we'll try and make this class a little useful. So we will start by defining an init function, which is a Dunder method, which we shall be looking at later on the series. We pass self and name as arguments, and self.name is equals to name. Now here, this init method is called a constructor. It runs automatically whenever a new object is created. Its purpose is to initialize the object's data. Now this part is where beginners actually get confused. Self refers to the current object being created. So when we write self.name, we are attaching the name directly to that specific object. Every object created from this class will store its own independent data. Now let's create actual objects from this blueprint. So for our first user, we go user1 is equals to user Dave, and for our user2, we go user Priya. So Dev and Priya are our two users. So if we run, these two users are created. Now if we print these two names, user1.name and print user2.name, we shall get Dev and Priya. Even though both our objects come from the same class, they store completely independent data. This is one of the biggest advantages of object-oriented programming. We define the structure once and create multiple independent objects from it. Now, so far, our objects only store data. Now, we'll try and give it some behavior. Now, first, we shall be implementing the greet method. So we pass self again, and we go print hello and self.name. Now let's try and implement another method, diff introduce self, and let's return a string instead, f I am, and then we go self.name. Now methods are simply functions defined inside a class, so they define what an object can do. Notice that every method takes self as its first parameter. That's because methods need access to the object's own data and attributes. Now let's try and call these methods. So I'll comment these out. So we have Dev and Priya. Now, when we go user1.greet, we go hello Dev. Now, when we go user2.greet, we go hello Priya. Now, when we call introduce, the introduce method returns a string with im self.name. Now, Python automatically passes user1 as self. So inside the method, self.name becomes Dave. Each object calls methods using its own internal data. Now let's quickly recap the key concepts from this video. A class is the blueprint. An object is an instance created from that blueprint. Attributes store data on the object. In our example, name was an attribute. Methods define behavior, and self refers to the current object itself. These concepts form the foundation of object-oriented programming in Python. Now, in the next video, we'll explore class attributes and instant attributes and understand the difference between shared data and object-specific data. As this series progresses, you'll gradually build a much deeper understanding of object-oriented programming in Python. If you found this video useful, consider subscribing for more Python and software engineering content. Thanks for watching, and I'll see you in the next video. Hello everyone. Welcome back to the Python OOP series. In the previous video, we learned the foundations of OOP in Python. We talked about classes, objects, methods, and the very important self keyword. Today, we are going to learn another important concept that every Python developer should understand: class attributes and instance attributes. One of the most common beginner mistakes is not knowing where data should be stored. Should a value belong to a specific object, or should it be shared across all objects? By the end of this video, you'll know exactly when to use instance attributes and when to use class attributes. So let's get started. Before we move forward, let's quickly review what we learned previously. A class is a blueprint that defines the structure and behavior of objects. An object is an instance created from that blueprint. Attributes are pieces of data stored on an object. Methods are functions defined inside a class, and self refers to the current object itself, allowing us to access that object's attributes and methods. These concepts form the foundation of OOP in Python. Now that we understand what attributes are, let's answer an important question. Where should those attributes actually be stored? Imagine we are building an application with thousands of users. Some information might be unique to each user. For example, their name, email address, age, date of birth, etc. But other information might be exactly the same for everyone. For example, the company name, the application version, or the platform name. Should every object store its own copy of those shared values, or should they exist once and be shared by all objects? The answer depends on whether we're using instance attributes or class attributes. Alright, so now we're starting with the code. So we'll implement the same class that we used in the last video. So class user, and then we define our constructor init self comma name. Now we go down and we initialize self.name is equals to name. Alright, so this is our user class. Now let's start with instance attributes first. An instance attribute belongs to a specific object. Whenever we create an attribute using self inside the constructor, we are creating an instance attribute. In this example, self.name is an instance attribute. For every object created from this class, will have its own independent copy of name. Now, we'll be initializing similar examples to our last video. So user1 is equals to user Dev, and user2 is equals to user Priya. So Dev and Priya are our two class names. Then we print these user1.name, just like we did in the last video. Print user2.name. Now Python main.py. I apologize. Yes, so we get Dev and Priya. Notice that user1 stores Dev and user2 stores Priya. Even though both objects come from the same class, they hold different values. Now let's prove that these values are completely independent. Now, if we go, I'll comment these out. User1.name is equals to Alex, and we print the names again, we'll get something else. We get Alex and Priya. So as you can see, when we change user1's name, user2 name remains unchanged. That's because instance attributes belong to individual objects. Each object manages its own copy of the data. Now we shall be having a look at a different situation. Suppose every user belongs to the same company. Storing the company name inside every object would be wasteful because the value is identical for everyone. Instead, what we can do is we can store that value once inside the class itself. This is where class attributes become useful. Now, we shall be implementing the class attributes. Now let me go. Company is equals to Tech Corp. Notice that company is defined directly inside the class and outside any method. This makes it a class attribute. Now, let me comment this out first. Print user1.company, print user2.company. Now if I go python main.py, we see that TechCorp is printed twice. We can see that both objects can access the company attribute. However, neither object stores its own copy. Instead, they're accessing a shared value that belongs to this class. Now, let me comment this out again. I go print user.company. If I run, we can see that TechCorp is printed once. This shows us that the class itself owns this value. The object simply accesses it through the class. Now, let me comment this out again. If I go user.company is equals to Google. Now, if I print user1.company, and if I run this code again, we get Google. Notice what happened here. We changed the value on the class itself, and immediately every object sees the new value. This is the biggest advantage of class attributes. Now, let's compare the two side by side. Instance attributes belong to an object. Class attributes belong to the class. Instance attributes are stored separately for every object, while class attributes are shared across all objects. Instant attributes can have different values for different objects, while class attributes usually represent information that should remain consistent across all objects. Now, in practice, instance attributes are used for data that's unique to each object. Now, examples are name, email, age, account balance, user ID, etc. While class attributes are used for data that should be shared. Now, examples are company name, application version, tax rate, app name, etc. A simple rule is this: if every object should have its own value, use an instance attribute. If all objects should share the same value, use a class attribute. Now, let's have a look at a common beginner mistake. Now, let me remove this all out. Now, let me initialize the class again. Class user company is equals to Tech Corp. Tech Corp. Now, I'll initialize user1 this way. Now, say I want to edit the company. User1.company is equals to Google. What do you think will happen here? Now, let me show you what happens by printing everything. Now, user1.company and print user.company. If I run this, you can see that user1.company prints Google and user.company prints Tech Corp. Many beginners expect both values to become Google, but that's not what happened here. When we assigned a value to user1.company, Python created a brand new instance attribute on that object. The original class attribute remained unchanged. This is one of the most important things to understand when working with class attributes. Now, let's summarize what we've learned in this video. Instance attributes belong to individual objects. Every object has its own copy. Class attributes belong to the class itself. All objects share the same value. Whenever you're deciding where data should be stored, ask yourself one question. Should every object have its own value? If yes, use an instance attribute. Should all objects share the same value? If yes, use a class attribute. Now, that's it for today. In the next lesson, we'll learn about encapsulation in Python and understand how to control access to data inside our classes. If you found this video useful, consider subscribing and following the series. Thanks for watching, and I'll see you in the next video. Hello everyone, welcome back to the Python OOP series. In the previous video, we learned about class attributes and instance attributes. Today, we're going to learn about another fundamental OOP concept, encapsulation. Encapsulation is all about controlling access to data inside an object. Instead of allowing anyone to modify important information directly, we can control how that information is accessed and updated. By the end of this video, you'll understand public attributes, protected attributes, private attributes, getter and setter methods, and Python's name mangling mechanism. Now, let's get started. Now, before we move forward, let's quickly review what we've learned so far. We know that classes are blueprints for creating objects. Objects are instances created from those classes. We also learned about instance attributes, which belong to individual objects, and class attributes, which are shared across all objects. These concepts form the foundation of OOP. Today, we're going to build on them by learning how to access data inside our objects. Now, what is encapsulation? Encapsulation is the practice of controlling access to an object's internal data. Instead of exposing everything directly, we decide what should be accessible and what should remain protected. Why is this important? Because it helps prevent accidental mistakes. It helps us keep data valid. And it also makes our code easier to maintain. Let's have a look at this with an example. Now let's start by implementing a bank account class. Let's start by typing class bank account. We initialize our constructor, self keyword is passed, and we pass a balance variable. Self.balance is equals to balance. Now everything looks fine, but the problem is that balance is completely public. If I go account is equals to bank account with a value of 1000, and I print account dot balance, and I go here Python main dot py, I get 1000 as my answer. Here everything is fine, but if we try and modify the bank balance, it is modified. So if I go account dot balance is equals to minus 5000, and I go print account dot balance, if I run this again, as you can see, the new account balance is now 5000. This should not be allowed, but because the attribute currently is public, any part of our program can modify it directly. There's no validation, no protection, no safety checks. This is exactly the problem encapsulation tries to solve. In Python, there are three common levels of access: public attributes, protected attributes, and private attributes. Let's see all three in action. Now here, we have a user class where name is a public attribute, email is a protected attribute, and password is a private attribute. Now email has 1 underscore before it and password has 2 underscores before it. Now if we go print user.name and print user.email, if I run this code, Python main.py, you can see Dave and dave@gmail.com have been printed. Notice that both public attribute and protected attribute can be accessed directly. Let's understand what each access level is actually used for in real applications. Now this is a public attribute. Public attributes are intended to be accessed directly by other parts of the program. In production code, public attributes usually represent information that is safe and is expected to be exposed. Now the examples include a product name, a username, a title, or display information. For example, if we're building an e-commerce application, it would be perfectly normal to access a product's name directly. Public attributes are essentially part of the class's public interface. Now, this underscore email is a protected attribute. Protected attributes use a single underscore. Python still allows us to access them directly. The underscore is simply a convention. It tells other developers this attribute is intended for internal use only. Now, what does internal use actually mean? It means that this attribute is primarily expected to be used by methods inside the class itself, or by classes that inherit from it. We will understand inheritance later on in the series. For example, a class might store cache data, internal configuration, framework state, or implementation details using protected attributes. External code can still access these values, but the underscore acts as a warning that these attributes are not really a part of the public interface of the class. Python relies on developer discipline here rather than strict enforcement. Now, the most important, user.password. Now, let's try and print user.password dot double underscore password. If I run this, python main.py, we get an error. This is a private attribute. Private attributes use a double underscore. Python applies a mechanism called name mangling to make accidental access much harder. Private attributes are commonly used when a class needs strong control over important internal data. In production systems, private attributes are often used for passwords, authentication tokens, account balances, connection state, encryption keys, and other implementation details that should not be modified directly. For example, in banking applications, we don't want any piece of code to arbitrarily change a customer's balance. Instead, updates should happen through control methods such as deposit or withdraw. Private attributes help enforce these rules. So now, we've seen the three levels of access: public for information that should be accessible, protected for information intended mainly for internal use, and private for information that requires strong control and validation. Now, we shall be having a look at getter and setter methods. Now let's remove this code completely and initialize a bank account class. Now let's initialize our constructor self and balance like before. We go self dot underscore underscore balance is equals to balance. Now balance here is a private attribute. Now on the same class we write def get balance, get balance, and we pass self as usual. Now we return self dot underscore underscore balance. Now again we write def set balance, we pass self again, and if amount is greater than or equal to 0, we pass self dot underscore underscore balance is equals to amount. Alright, we didn't pass amount as an argument. Right. Now instead of accessing private data directly, we can use these methods. A getter method provides controlled read access, and a setter method provides controlled write access. Now let's try and use these methods. Now account is equals to bank account. Now let's initialize with a value of 1000. Now if I go print account dot get balance, and if I run this code, let me clear first, main python main.py, we get 1000. Now let's test our validation. If I set balance, say, let me comment this out. If I account dot set balance of minus 5000, and then I run this code again, the balance didn't change. The setter rejected the invalid value. So this is one of the biggest benefits of encapsulation. We can enforce rules before data is modified. I could also use else print invalid amount. Now if I run this code, says invalid amount. Now, you might be wondering what actually happens behind the scenes. If Python prevents direct access, where is the data stored? Alright, so now let me comment this out and let's try and see what happens when we try to access private attributes again. So if I go print account dot underscore underscore balance, and if I run this code, we get an error. Now, if we replace this, let me comment this again. If I go print account dot underscore bank account, which is our class name, underscore underscore balance, and if I run this code, we can see that we got our bank balance. Now this is quite interesting because the value still exists and Python did not truly hide it. Instead, Python renamed the attribute internally. The attribute double underscore balance becomes underscore bank account double underscore balance. This process is called name mangling. Its purpose is not security. Its purpose is to prevent accidental access and accidental naming conflicts. Now, encapsulation appears everywhere in real software. In banking systems, it prevents invalid balances. In healthcare systems, it helps protect sensitive patient information. In user management systems, it protects personal information and credentials. In API clients, it hides internal configuration and implementation details. Whenever data requires protection, validation, or controlled access, encapsulation becomes useful. Now, let's summarize everything we've learned today. Public attributes use attribute. Protected attributes use underscore attribute. Private attributes use double underscore attribute. Getter methods provide safe read access. Setter methods provide validated write access. And Python implements private attributes using a mechanism called name mangling. Encapsulation helps us build safer, cleaner, and more maintainable software. Now that's it for this video. In the next video, we'll learn about inheritance in Python. We'll see how one class can inherit functionality from another class, allowing us to build reusable and extensible software. If you found this video useful, consider subscribing and following the series. Thanks for watching, and I'll see you in the next lesson. Hello, and welcome back to the Python OOP series. In the previous video, we learned about encapsulation, different types of attributes, getters, setters, and how to protect an object's internal data. Today, we will be moving into another fundamental pillar of object-oriented programming called inheritance. Inheritance allows us to create new classes based on existing classes. Instead of writing the same code over and over again, we can build on top of classes we've already created. This is a concept you'll see everywhere in production software, whether you're building banking systems, healthcare platforms, e-commerce applications, or machine learning systems. By the end of this video, you'll understand what inheritance is, why it exists, how to create subclasses, and how Python finds methods using something called method resolution order, or MRO. Now, let's start with the problem inheritance solves. Imagine you're building a company management system. You create an employee class containing a name, email, and an employee ID. Now the business needs developers, then managers, then HR employees. Without inheritance, you'd end up copying the same attributes and methods into multiple classes. This creates duplicated code. Duplicated code is expensive because every future change must be repeated in multiple places. Experienced software developers and engineers try to avoid this duplication whenever possible. Inheritance exists to solve this problem. It allows a child class to reuse functionality from a parent class while still adding to its own behavior. So, what exactly is inheritance? Inheritance is a mechanism that allows one class to acquire attributes and methods from another class. The original class is called the parent class. You may also hear terms like base class or a superclass. The new class is called a child class or a subclass. The child automatically gains access to everything defined in the parent. Now, why is this useful? Because software systems often contain objects that share common functionality. Rather than rewriting the functionality over and over, inheritance allows us to define it once and reuse it everywhere. This leads to a cleaner code base and easier maintenance. When deciding whether inheritance should be used, experienced engineers and developers often ask one simple question: does an is-a relationship exist? For example, A developer is an employee. A manager is an employee. An admin user is a user account. These are valid inheritance relationships. Now consider this example. A user account has a password. That is not and is a relationship. A user account is not a password. That has a relationship. A common beginner mistake is using inheritance where composition should be used instead. Inheritance should only be used when the child is a more specialized version of the parent. Now, we shall be implementing an inheritance example. Here, we'll create a user account class and then create an admin user that inherits from it. This is much closer to what you'd see in a real application. So we go class user account. Now we define a method login, pass self, and print user logged in. Now we create another class called admin user. We open the parentheses and we send user account as the parent class and we pass. Now what we can do is we can create an admin user object, and if we call admin.login, if I run this code, we can see that user is logged in even though nothing is defined here in admin user. This is because the admin user class, which is the child class, has access to everything the parent class consists. Now we can implement whatever function here as well. Def logout, we call self, we simply print user logged out. Now if we call admin.log out and we print, we get user logged in and user logged out. However, let's create a user object and let's call user.logout. Let's see what happens here. We get an error saying user logout object has no attribute logout. This means that the parent has no access to the child's methods. However, the child does have access to the parent's method. Now, what we just saw is called method inheritance. The login method only exists inside user account. However, admin user can still use it. This becomes extremely useful in production systems. For example, you might have user account, admin user, customer user, and support user. All of them can inherit common functionality such as login, logout, password reset, profile updates, etc. Instead of writing those methods multiple times, they can live in one parent class. This reduces maintenance and improves consistency across the system. Now, how does Python search for methods? Now, Python follows a specific search order. First, it checks the child class. If the method isn't found there, Python moves to the parent class. If it still isn't found there, Python continues moving upward through the inheritance hierarchy. The search path is called the method resolution order, or MRO. Understanding MRO becomes very important once you start working with larger applications and more advanced inheritance structures. Now, let's see what method resolution order actually looks like. Now, let me comment these out and let me write print admin user dot double underscore MRO double underscore. Now, MRO is a Dunder method, which we shall be looking on further in the series. Now, if I print this, this is what I get. Now, Python tells us exactly where it will search. First, it will search the admin user, then user account, then the built-in object class. This means if Python cannot find something in admin user, it automatically moves up to user account. And if it still can't find, it checks object. Experienced engineers often inspect the MRO when debugging complex inheritance hierarchies because it reveals exactly how Python resolves methods. Now, let's have a look at a common AI application example. Imagine you're building a machine learning platform. I presume everyone knows what machine learning is at this point. We create a base model class. The model class might contain functionality such as a train method to train the model, a save method to save the model, or a load method to load the model. Here, we create our own specialized models as children class, such as a classification model, a generator model, a recommendation model, a regression model, etc. All of these are models. This means that they can inherit common functionality from the parent class, which is model. The specialized classes only need to implement features unique to themselves. This approach is heavily used in frameworks such as TensorFlow, PyTorch, and many enterprise-grade machine learning platforms. Inheritance helps developers build scalable systems without constantly rewriting the code. Now, let's quickly recap what we've learned today. Inheritance allows one class to reuse functionality from another class. A parent class provides common functionality. A child class inherits that functionality. Inheritance should model and is a relationship. Python uses the method resolution order or MRO to determine where methods should be searched. And inheritance is widely used in real-world software systems to reduce duplication and improve maintainability. Now, in this lesson, we learned how inheritance allows child classes to reuse functionality from their parent classes. We created our first subclass, saw inherited methods in action, and learned how Python searches through the inheritance hierarchy using MRO. In the next video, we'll make inheritance even more useful by learning method overriding and the super function. We'll see how child classes can customize parent behavior while still reusing existing code. I'll see you in the next lesson. Hello, and welcome back to the Python OOP series. In the previous lesson, we learned about inheritance and how child classes can inherit attributes and methods from their parent classes. But inheritance alone is not enough. In real software systems, child classes often need to behave differently from their parent classes. For an example, an admin user might log in differently from a regular user account. In banking systems, a savings account might charge fees that a regular bank account does not. This is where method overriding comes in. We'll also learn about the special super function, which allows child classes to reuse parent functionality without duplicating code. By the end of this lesson, you'll know how professional software engineers customize inherited behavior while keeping their code clean and maintainable. Now, let's start with the problem. Now, inheritance only allows classes to inherit everything from their parent classes. That is useful, but sometimes a child class shouldn't behave exactly like the parent. Consider a user account. It has a login method. Now imagine an admin user. Should administrators log in exactly the same way as normal users? Probably not. Administrators often require additional security checks like multi-factor authentication, additional permissions, or verification steps. The child class still wants most of the functionality from their parents, but still needs to customize certain parts. That's the motivation behind method overriding. So, what is method overriding? Method overriding occurs when a child class provides its own implementation of a method that already exists in the parent class. When Python sees a method call, it checks the child class first. If the child class has its own version, Python uses that version. The parent method is effectively replaced for the child class. This allows specialized behavior while still benefiting from inheritance. Let's see this in code. Alright, so now let's implement a user account class. So we go class user account. We implement a login method. We pass self and we print user login. Now we implement a child class called admin user, just like we did in the previous video. We define login again, pass self again, and we print admin user login. Now let me create two objects, user account and admin user. Now we have two objects. Now let me just call the two methods admin dot login. Now let's go here, Python main.py. I apologize. As you can see, user login and admin user login have been printed. The user object used the login method defined inside user account, and the admin user used the login method defined inside the admin user. Even though both classes have a method with the same name, Python chooses the version that belongs to the object class. This is method overriding in action. Now let's have a look at some real-world examples. In banking systems, a bank account may have standard withdraw method. A savings account might override that method to include transaction fees. In authentication systems, a user account may have normal login process. However, an admin user might override login to require additional verification. In API integrations, a base API client might send requests one way, while OpenAI client or Gemini client override parts of that behavior to handle provider-specific requirements. Experienced engineers use overriding whenever a child class needs specialized behavior that differs from the parent. Now, let's discuss a common mistake. Suppose user account already contains username handling, email storage, password verification, and authentication login. Should admin user rewrite all of that code? No, absolutely not. Copying and pasting code creates duplication. Duplicated code becomes harder to maintain because every future change must be made in multiple places. Professional engineers avoid duplication whenever possible. Instead of rewriting existing functionality, we want to reuse it and only add what's different. That's exactly what super helps us to do. Now, super gives us a child class access to methods and attributes from its parent class. Think of it as saying, run the parent version first, then let me add my own behavior. Why does this exist? Because most of the time, child classes don't want to completely replace parent functionality. They only want to extend it. Super allows us to reuse existing logic rather than rewriting it. This reduces duplication and keeps code easier to maintain. Now, one of the most common places you will see super is inside constructors. Let's build a realistic example. Alright, now in these very classes, let me remove this part. We'll use the same classes. I'll remove login as well. We'll define our constructor and we'll pass self and username. Now, self.username is equals to username. Alright, now in admin user, let's define our constructor again. Now, we'll also pass a role parameter, self.role is equals to role. Now, let's understand what's happening. When admin user is created, let's create an admin user first. Admin is equals to admin user. Now we'll pass name dev and developer. Now let's print, for added understanding, admin.username and print admin.role. Let's run this. We get dev and developer. Now let's understand what's happening. When admin user is created, Python enters the admin user constructor. The first thing we do is call super init and username. This tells Python to execute the parent constructor. The parent constructor creates the username attribute. After that finishes, admin user adds its own role attribute. Without super, we'd have to manually update the parent's initialization logic to the child class. As applications grow larger, that duplication becomes a maintenance problem. This is why super is heavily used in production systems. Now, constructors are not the only place where super is useful. We can also use it inside normal methods. Now let's implement the login methods again. Login, pass self, and then we print login user account. Now On the admin user side, we define login again. We pass self. We pass the super login for our login method, and then we print something else. Print performing additional verification for admin. Alright, now admin user is created. If I go admin dot login, let me clear this first. If I run this code again, python main.py, you can see login user account and performing additional verification for admin has been printed. Now, as you can see, there's a difference. We are not replacing the parent method, we are extending it. The standard login process still happens here. However, our added functionality also runs. This pattern appears everywhere in enterprise software because it lets developers build on existing functionality instead of throwing it away. Now let's look at a software architecture example. Imagine building multiple AI integrations. You create a base API client that handles authentication, request handling, and error handling. Then we create an OpenAI client, a Gemini client, and a Claude client. Each provider inherits from the API client. Shared logic remains in one place. Provider-specific behavior can be overridden when necessary. This architecture is easier to maintain, easier to test, and much easier to scale than copying the same code into every client. Say there is another client, for example a Grok client, to be implemented again. We can follow the same process. This is exactly how inheritance, overriding, and super are used in many production systems today. Now let's do a quick recap. Today, we learned that child classes can override parent methods to create specialized behavior. We learned that Python checks the child class first when resolving methods. We learned that super allows us to reuse parent functionality instead of duplicating code. And we saw how these concepts are used in real software systems. In the next lesson, we'll explore the different types of inheritances available in Python. We'll cover single inheritance, multi-level inheritance, hierarchical inheritance, and we'll also revisit MRO, which is method resolution order, and see how Python resolves methods across more complex inheritance hierarchies. If you found this video useful, make sure to like the video, leave a comment, and subscribe for the next lesson in Python OOP series. Thanks for watching, and I'll see you in the next video. Welcome back to the Python OOP series. In the previous lesson, we learned about method overriding and the super function. Today, we're going to expand our understanding of inheritance by looking at the different ways inheritance can be structured. Many beginners think that inheritance is always one parent and one class. But in reality, software systems use several inheritance patterns depending on the problem being solved. We'll cover single inheritance, multi-level inheritance, hierarchical inheritance, multiple inheritance, and finally, method resolution order or MRO. Understanding these patterns will always help you read and design larger object-oriented systems with confidence. Now, inheritance allows classes to reuse code. But real-world software systems don't always have the same class structure. Sometimes, one child inherits from one parent. Other times, inheritance is a chain. Sometimes, multiple child classes share the same parent. And other times, a single class inherits from multiple parents. Python supports all of these structures. Think of inheritance as a family tree. Not every family tree looks the same, and not every software architecture looks the same either. Let's start with the simplest form of inheritance. So single inheritance is the simplest and most common type of inheritance. A child class inherits from exactly one parent class. This is the form you'll encounter most often in beginner and intermediate Python projects. Let's see an example. Alright, so now we're implementing a user account class and its child, an admin user class. So we go class user account, and then we add a login method with self, and we basically print user logged in. Now we make a child class admin user, we pass user account, we simply pass. We don't implement anything else. Now we create an object of admin user and we pass admin dot login. Alright, now let's print main.py. We get user logged in. Now we've seen these kind of examples in our previous videos as well. Admin user inherits from the user account. When Python cannot find login inside the admin user, it checks user account and finds it there. This relationship is straightforward, easy to understand, and easy to maintain. That's why single inheritance is the most commonly used inheritance structure in production code. Now some real-world examples include user account to admin user, employee to developer, product to digital product, etc. Whenever one class is simply a more specialized version of another, single inheritance is often the best choice. Now, let's move one step further. Multi-level inheritance occurs when a class inherits from a class that already inherited from another class. Instead of one parent and one child, we create a chain, a grandparent, parent, and a child. Let's switch to code. Alright, let me clear all of this. Let me implement a user class. We define a method called access system, pass self, and print system access granted. We make another class staff and we pass user, we pass, and we make another class administrator. We pass staff, and we pass again. Now, as you can see here, staff is the parent of administrator and user is the parent of staff. So now we make an object for administrator and we type admin.accessSystem. Now if I run this code, let me put this up a little. System access granted has been displayed. Notice what happened here. Administrator doesn't define access system. Staff doesn't define it either. Python keeps moving upwards through the inheritance chain until it finds the method in the user. This is called multi-level inheritance. It is useful when functionality becomes progressively more specialized. However, experienced engineers usually avoid making inheritance chains too deep because they become harder to understand and maintain. Now, as you can see here, there's a given example. The grandparent is employee, parent is developer, and the grandchild is senior developer. Each level adds more specialization while reusing functionality from levels above. Now, another type is hierarchical inheritance. Hierarchical inheritance is extremely common in large applications. Here, multiple child classes inherit from the same parent class. This allows common functionality to live in one place while different child classes add their own features. Let's have a look through code. Alright, let me remove all of this again. We go class employee access portal self, and then we go print accessing portal. Then we define two more classes, class developer, we pass employee, we pass, and class manager. Let's say we pass employee again as manager is an employee too, and we pass again. Now let's go developer is equals to, this is auto corrected, developer manager is equals to manager. Now we can go developer dot access portal and manager dot access portal. Now if we run this code, we get accessing portal printed twice. Here all two classes inherit the same functionality. Instead of duplicating access portal 2 times, we define it once in employee. This reduces duplication and makes future updates easier. A production example for hierarchical inheritance would be an API client as the lead parent class, an OpenAI client for OpenAI's processing, Gemini client for Gemini's processing, and Claude client for Claude's processing. All three clients share common functionality from the same parent class, which is API client. Now, we arrive at the most powerful and sometimes the most confusing inheritance type, multiple inheritance. Now, multiple inheritance allows one class to inherit from multiple parent classes. This means that the child class can combine functionality from multiple sources. Let's switch to code again. Let me remove all this. Now, let's implement a camera class camera def take photo. Now we pass self and we print photo taken. Let's make another class phone def make call. We pass self again and let's print calling. Now let's make a class smartphone that shall inherit behavior from both of these classes, camera, phone. Now we go pass. Now let's make an object of this smartphone class and let's try calling both the methods. Now phone dot take photo and phone dot make call. Let's run this. As we can see, photo taken and calling have been printed. Now smartphone inherited functionality from both camera and phone here. This can be very useful. However, it introduces a new problem. What happens if both parent classes contain a method with the same name? Python needs a way to decide which version should be used. That we shall now have a look at how we solve that problem. Now the problem is defined as a method conflict problem. Instead of take photo and make call, let's name this both start and start. Alright, now let's print phone dot start. We run. We see here that photo taken has been printed. Interesting. Both camera and phone define start, yet Python only used the camera version. Why? Because Python follows a specific search order when looking for methods. This search order is called method resolution order or MRO. Now, MRO determines the exact sequence Python follows when searching for methods and attributes. Let's inspect this directly. Alright, let's change this completely. Let's pass and pass here. And now let's go print smartphone dot double underscore MRO double underscore. Now let's run this code. Now here Python tells us exactly how it searches. First, it goes through smartphone, then it goes through camera, then it goes through phone, and then it searches the object. Since camera appears before phone, Python uses camera's version of start first. Here, camera is to the left of phone, meaning camera appears before phone. This makes method resolution order predictable and prevents ambiguity in multiple inheritance scenarios. These inheritance patterns aren't just classroom concepts. They're used every day in production software. Single inheritance is common for user management systems. Hierarchical inheritance is common for API clients and backend services. Multiple inheritance is often used with mixins to add reusable functionality. Inheritance helps a team to reuse code, maintain consistency, fix bugs faster, and to build new features more quickly. However, experienced engineers use inheritance very carefully. As systems grow, overly complex inheritance hierarchies can become very difficult to manage. That is why Understanding these patterns is important before using them in production. Now, let's recap. Today, we learned single inheritance, multi-level inheritance, hierarchical inheritance, multiple inheritance, and method resolution or MRO. You now understand the major inheritance structures available in Python and how Python resolves methods when multiple parents are involved. In the next lesson, we'll explore one of the most important object-oriented concepts, polymorphism. If you found this video helpful, like the video, leave a comment, and subscribe for our next lesson in Python OOP series. Thank you, and I'll see you in the next lesson. Hello, and welcome back to the Python OOP series. In the previous video, we learned about inheritance and different types of inheritance. Today, we are going to learn one of the most important concepts in object-oriented programming called polymorphism. This concept is heavily used in backend development, large software systems, frameworks like Django, and even in machine learning libraries such as scikit-learn. By the end of this video, you'll understand what polymorphism is, why engineers use it, and how it helps us write cleaner and more scalable code. So let's get started. Now, before we talk about polymorphism, let's quickly recap what we've learned so far. Inheritance allows child classes to inherit attributes and method from their parent classes. Method overriding allows a child class to provide its own implementation of an inherited method. When we combine inheritance and method overriding together, we get polymorphism. You can think of it like this. Inheritance creates the relationship, and method overriding creates different behaviors. Polymorphism allows us to use those different behaviors through a common interface. Keep that idea in mind because everything in this video builds on it. Now, what is polymorphism? Now, polymorphism comes from two Greek words. Poly means many and morph means forms. So polymorphism literally means many forms. In programming, polymorphism means that the same method call can behave differently depending on the object receiving that call. The method name is the same, but different objects can perform different actions. This allows us to write code that focuses on what an object can do instead of worrying about exactly what type of object it is. This makes software more flexible and easier to extend. One interesting thing is that you've already been using polymorphism since you started learning Python. Take a look at these examples. Len hello returns 5. Len 123, which is a list, returns 3. The same function is being used, but Python behaves differently depending on the object. Let's look at another example. 10 plus 20, which are of type integers, both values, return 30. Hello plus word, which are strings, return hello world. The plus operator is the same, but it performs different operations depending on the data type. That's polymorphism. Same interface, different behavior. Now let's see how polymorphism works in object-oriented programming. Imagine we're building an online payment system. We have a parent class called payment. Then we have 3 child classes, credit card, PayPal, and bank transfer. All of them have a method called process payment. The method name is identical, but the implementation is different. A credit card payment needs card validation. PayPal requires authentication. A bank transfer may require communication with the bank API. Same method, different logic. That's polymorphism through inheritance. Now, let's have a look at polymorphism through code. Now let's try and implement a basic version of a production payment system. Now, let's make our first class, which is payment. Now, let's add a method called process payment. Pass self and print processing payment. Now, let's make another class, credit card, pass payment. Now credit card is the child of payment. Define process payment again. Now let's not return super. Write print, processing credit card payment. Alright. Now let's implement class PayPal. pass payment again. Now PayPal 2 is a child of payment. Define the process again and print processing PayPal payment. Now let's implement our final class, bank transfer. Pass payment again. Define the process again and print processing bank transfer. Now let's create some objects. Now we go payments is equals to a big bracket, credit card, PayPal, and our final bank transfer. Notice that all these objects are stored inside the same list. That's possible because they all share the same interface. Now let's use polymorphism. Now let's write a loop for payment in payments. Payment dot process payment, and then we run the code. Let me open my terminal, type python main.py, which is my file name. As you can see, our output is processing credit card payment, processing PayPal payment, and processing bank transfer. This is the moment where polymorphism becomes powerful. Look carefully. We never wrote if instance or any kind of if statement. We never checked the class type. We simply called payment.processPayment. Python automatically determined which version of the method should run. For credit card object, Python called the credit card version. For PayPal object, Python called the PayPal version. And for the bank transfer object, Python called the bank transfer version. One method call, 3 different behaviors. This is polymorphism. Now let's talk about why experienced software engineers use polymorphism. Without polymorphism, code often looks like this, a bunch of if and else statements together. Now imagine in this example, the company decides to add Apple Pay, Google Pay, crypto, international wire transfer, and bunch of other payment methods. This would mean the conditional block or the if-else statements would keep on growing. The code then becomes much harder to maintain, and with polymorphism, all of that just becomes payment.processPayment, just like in our previous example or here. If tomorrow we create a new payment class, we don't have to modify the existing code. We simply create a new class and implement the method. This is one reason why polymorphism helps create scalable software systems. Now, since many of you are probably interested in AI and machine learning, let's see a real-world example. Imagine a machine learning pipeline. We may have different models, a random forest model, XGBoost model, a deep learning neural network model, etc. Even though the internal algorithms are completely different of these models, they often expose the same methods, for example, fit or predict. Now, the training pipeline does not need to know which model it's working with. It simply calls model.fit or model.predict, and each model performs its own implementation. This is exactly how production AI systems and machine learning libraries are designed. Polymorphism is not just a classroom concept. It is used every day in real software systems. Now, let's quickly recap. Polymorphism means many forms. The same method call can behave differently depending on the object. Polymorphism is usually achieved through inheritance and method overriding. It helps eliminate large if-else chains. It makes software easier to maintain and extend, and it's widely used in backend systems, frameworks, and AI applications. Now, in the next video, we'll learn about abstract base classes or ABCs and see how professional developers enforce rules and contracts between classes. If you found this video useful, make sure to like this video, subscribe to the channel, and let me know in the comments what OOP topic you found most interesting so far. Thanks for watching, and I'll see you in the next one. Hello everyone, welcome back to the Python OOP series. In the previous video, we learned about polymorphism and saw how the same method call can produce different behavior depending on the object receiving that call. But polymorphism has an important problem. What happens if a developer creates a new class and forgets to implement one of the required methods. The code might look perfectly fine, but the bug may not appear until much later when that class is actually used. Professional software systems try to catch these mistakes as early as possible. That is why abstract base classes, or ABCs, exist. In this video, you learn what abstract base classes are, why they exist, and how experienced software engineers use them to enforce rules between classes. Now, let's get started. Now, in the previous lesson, we learned about polymorphism. Polymorphism allows different classes to expose the same interface while providing different implementations. For example, a credit card, PayPal, and bank transfer class can all implement a method called process payment. We had a look at this example in the previous video as well. When we call that method, Python automatically executes the correct implementation for that object. This works great, but there is one huge problem. Python trusts developers to implement the required methods, and sometimes the developers can forget. That's where abstract-based classes come in. Abstract-based classes allow us to formally define what every child class must implement. Think of them as a contract between parent class and its subclasses. Now let's imagine we're building an online payment system, just like in the last video. We already have several payment methods. Everything works perfectly fine. Now, a new developer joins the team and creates a new payment method, say, crypto payment. At the very first glance, nothing looks wrong. The class exists, the code runs, but there might be a problem. The developer, if he forgets to implement process method, the required functionality is missing. Without a proper contract, Python might not discover this mistake until the class is actually used. Maybe the bug appears during testing, or it may appear during deployment, or maybe customer is the first person to actually discover it. That is not something we want in production systems. We want Python to tell us exactly and immediately when a class is incomplete. Now, so what exactly is an abstract base class? An abstract base class, or an ABC, is a special type of class that defines rules for its subclasses. Think of it as a blueprint. A blueprint tells a builder what a house must contain. It does not build the house itself. Similarly, an ABC tells child classes what methods they must implement. It creates a contract of some sort. If a child class does not follow the contract, Python raises an error. This allows us to catch problems much easier, earlier, and make our code base much more reliable. That is why abstract-based classes are common in large software systems, backend applications, and even in machine learning frameworks. Now, let's see how ABCs work. Before we continue to code, it is important to note that ABC is bundled inside the Python standard library. We do not need to install anything. Alright, now let's understand two very important components: ABC, abstract base class, and the abstract method. Let me start by typing from ABC import ABC and abstract method. Now, let's understand these two components. ABC allows us to create an abstract class. Abstract method allows us to mark methods as required. Together, they allow us to create contracts between classes. Now let's build one. Let's say implement class payment, pass ABC as its parent class, and use an abstract method decorator. We shall be understanding decorators later on in the series. For now, we'll just be using them. Process payment, pass self, and simply pass. Now, let's break this down. Payment inherits from ABC. That means payment is now an abstract class. Next, we use the abstract method decorator. This tells Python that process payment is required in every subclass, meaning every subclass must provide its own implementation of this method. Notice that there is no actual payment logic here. The class only defines the rule, a blueprint. It is not a finished product. Now, let's create some concrete implementations. Let's define our credit card class, just like in the last video. Credit card, and it is a child of the payment class. We define our own process payment method here. We remove and we print processing credit card payment. Now let's implement another class, say class PayPal, pass payment again, write everything, remove this, print processing PayPal payment. Let's implement our final class, class bank transfer, pass payment again, our final process payment method, remove this, and print processing bank transfer. Now each class follows the contract, each class implements process method, everything is valid. Now let's test our classes. Let's make objects for each class, say credit, so it goes to credit card, PayPal, so it goes to PayPal, and bank, so it goes to bank transfer. All right. Now let's use all the methods. Credit dot process payment, PayPal dot process payment, and bank dot process payment. Now let's run this code. Let me open my terminal and type python main.py. All right. Everything works exactly as expected. And because every payment method follows the same contract, we can safely use polymorphism. As developers, we know every payment method or payment object will contain process payment. We don't have to guess, we don't have to check. The contract guarantees it. This is one of the biggest advantages of abstract-based classes. Now, what if we forget it? Now, let's implement another class called crypto payment. Say class crypto payment, pass payment again, and simply pass. Now let's create an object for the crypto payment. So say crypto is equals to crypto payment. All right. Now let's run this code. As you can see, we get an error here. This is exactly what we want. Python immediately stops us. The error appears during development, not during production. Imagine discovering this issue while a customer is trying to make a payment. That would be a much bigger problem. ABCs move errors closer to the developer. And the sooner a bug is discovered, the cheaper it is to fix. That's how experienced engineers think about software quality. Alright, now let's have a look at a real-world AI example. Imagine you're building a machine learning platform. Your platform supports multiple models, say a random forest model, an XGBoost model, or a deep learning neural network model. Even though the algorithms are completely different, every model should support two operations: fit and predict. Here, we could create a model abstract base class requiring those methods. Then, every new model automatically follows the same interface. A training pipeline can safely execute model.fit and model.predict without caring which specific model is being used. This pattern is extremely common in machine learning libraries, backend services, MLOps platforms, and large software frameworks. ABCs make large systems more predictable and easier to maintain. Now, let's quickly recap what we learned today. An ABC stands for an abstract base class. An abstract base class acts as a blueprint for child classes. The abstract method decorator marks methods that every subclass must implement. ABCs create contracts between classes. They help catch mistakes early. They make software more reliable. And they're widely used in backend development, machine learning systems, MLOps platforms, and production software frameworks. Now, in the next video, we'll learn about Dunder methods and discover how special methods like len, str, and many other powerful Python's built-in functionality are implemented. If you found this video useful, make sure to like the video, subscribe to the channel, and leave a comment telling me where you think abstract-based classes would be useful in a real project. Thank you for watching, and I'll see you in the next one. Hello everyone, welcome back to the Python OOP series. So far, in this series, we have learned about inheritance, polymorphism, and abstract base classes. Today, we're going to learn something that you've actually been using since the very first day you wrote Python code, even if you didn't realize it. We're talking about Dunder methods. Dunder stands for double underscore. These specialized methods allow your classes to integrate directly with Python's built-in functions and syntax. When you use print, len, additional operators, or even create an object, Python is often calling a Dunder method behind the scenes. By the end of this video, you'll understand what Dunder methods are, why they exist, and how professional developers use them to make their objects behave like native Python objects. So let's get started. Now, before we jump into Dunder methods, let's quickly recap. We started with inheritance, where child classes inherit behavior from parent classes. Then we learned polymorphism, where the same method call can produce different behavior depending on the object. After that, we learned abstract base classes, which allow us to enforce contracts between classes. Today, we will be talking about another step, a step deeper into Python itself. We're going to learn how Python allows custom classes to interact with built-in language features through the Dunder method. So, what are Dunder methods? The word Dunder is short for double underscore. A Dunder method is a special method whose name starts and ends with two underscores. Now, there are multiple examples. For example, double underscore init, double underscore str, which stands for string, repr, len, etc. These methods allow your objects to hook into Python's built-in behavior. Think of them as communication points between your class and the Python interpreter. Without Dunder methods, your objects are just ordinary objects. With Dunder methods, they can work with print, len, operators, iteration, comparisons, and many other Python features. That's why Dunder methods are fundamental to writing professional Python code. Now, the interesting thing is that you've already used Dunder methods many times. Let's look at a few examples. When you write print obj, Python actually calls obj dot double underscore str double underscore. When you write len obj, the same thing happens. When you add two variables a and b, you get a dot add is a Dunder method, b. And when you create an object user, Python automatically calls user and calls its constructor. Python syntax is often just a cleaner way of calling Dunder methods. Understanding these methods makes Python feel much less magical. Now, let's start with the most common Dunder method, the init method. Alright, so let's implement our class user account and initialize our constructor with a username. Let's pass username first. Self.username equals to username. Now we can go print. Let's do this. Self, and we print the self dot username, and let's type initialized. Alright. Now let's create an object. We go user is equals to user account. Now let's write Dave. Alright. Now the expected output is user Dave initialized. Let's run this code. Python main.py. I apologize. User Dave initialized. Now, what happened here? When we created the object, Python automatically called the init method. Its job is to initialize the object. This is where developers typically create attributes, set default values, validate input, configure object state, etc. In production system, init is used everywhere. Django models, API clients, database connections, machine learning models, and nearly every object-oriented system relies on it. Now, let's create a product class. Let's go class product. Now we write our constructor again, and let's go self.name, but let's pass name first, comma name, and our product has a price is equals to name, and self dot price is equals to price. All right, now let's create an object and print it again. Let's go product is equals to product. We can say laptop, and the price is 120,000. Now let's go print product. All right, now let's run this code. Let's comment this out first. As you can see, the product object and its memory location has been printed. This is the memory location. Now this isn't very useful. Python is showing us the class name and the memory address. That's fine for the interpreter, but it's not really friendly for users or developers. So how do we fix this? Now we use another Dunder method called str, which stands for string. Now instead of printing this, we want something else to be printed. So we go str and we return, say, let's return f self dot name, and let's say price is self dot price. All right, now let's run this. As you can see, laptop price is 120,000. I made an error here, not an error, but a simple. All right, let's run this again. Perfect. Now, using str, this is how we do it. The expected output is laptop and 1200 as we saw, and this is much better. The str method controls what users see when an object is printed. Experienced developers use str to create clean, human readable output. Now, this is extremely useful for many things, such as logging, and for dashboards, admin panels, command line tools, etc. The goal of str is to help humans understand the object quickly. Now, let's look at another important Dunder method, repr. While str is for users, repr is primarily for developers. It helps developers look inside the code, what is happening. Now, in the product again, let's write, let's comment the str method for now, and let's define our repr. Double underscore repr. All right. Now we can return f product name is, let's go self dot name, or let's not do this. Let's go product self dot name, comma, and let's just print our price. Or not print, return our price. All right. Now let's test this. If I go, instead of print product, if I go print repr and product, sorry. All right. Let me clear this. And if I run this code, I get whatever repr had. Now, notice how this implementation is more technical. Ideally, repr should contain enough information for a developer to correctly understand what an object is and what they are looking at. This is incredibly useful for debugging, logging, error tracking, developer tools, etc. Now, many professional frameworks rely heavily on well-designed repr methods. Now, at this point, you must be wondering, why does all of this matter? The answer is simple. Dunder methods make custom objects behave like built-in Python objects. They improve debugging, they improve readability, they make code more Pythonic, and they allow developers to integrate seamlessly with Python's language features. Frameworks and libraries such as Django, NumPy, Pandas, and PyTorch, especially PyTorch, for which I shall make a series later in time, all rely heavily on Dunder methods internally. Understanding Dunder methods helps you understand how Python itself works. Now, let's have a quick recap of this lesson. Dunder stands for double underscore. Dunder methods are special methods that allow your classes to interact with Python's built-in syntax and functions. The init method initializes objects when they are created. The str method creates a user-friendly output. The repr method creates developer-friendly output. These methods make your classes feel like native Python objects. In the next video, we'll continue exploring Dunder methods by learning about len and getitem, and we'll make our own objects behave like lists. If you found this video useful, make sure to like the video, subscribe to the channel, and leave a comment telling me which Dunder method you found most interesting. Thanks for watching, and I'll see you in the next one. Hello everyone, welcome back to ML Orbit. In the previous video, we learned about Dunder methods and saw how Python uses special methods like init, str, and repr behind the scenes. Today, we're going to take that idea even further. We're going to make our own custom Python objects behave like built-in lists. We'll learn how functions like len work, how indexing works, and how Python allows us to customize these behaviors using two powerful Dunder methods, len and getitem. By the end of this video, you'll understand how libraries like Pandas, NumPy, PyTorch, and Django make their objects feel like native Python collections. Let's get started. Now, in the previous lesson, we learned that Python syntax often maps directly to Dunder methods. Now, when you create an object user, Python calls init. When you print an object, print obj, Python calls str. And when you use repr to obj, Python calls the repr method. Today, we'll discover that exactly the same thing happens with len object and object index. These operations are also powered by Dunder methods. Now, this might not make much sense right now, but I promise you it will later on. Now, can custom objects behave like lists? Let's imagine we're building a product catalog class. Internally, the catalog stores products. Naturally, users might expect to write len catalog to get the number of products, or catalog and index with 0. This gives the first items access. Now, these operations work perfectly fine on Python lists. Can we make them work on our own classes? Yes or no? The answer is yes. And the secret is Dunder method. Now, let's get started with the len function. Most beginners think len is special, but behind the scenes, Python is simply calling a Dunder method. When we write len catalog, Python actually executes catalog dot and Dunder method for len. This means that if we define len inside our class, Python automatically knows how to calculate its length. If we don't define it, Python raises an error because it has no idea what length means for our custom object. Now, let's switch to code. Alright, here, like we previously mentioned, we'll be implementing a product catalog class. Product catalog. And we define our constructor def init. Self. And we go self.products is equals to, and we define a list with, say, laptop, mouse, and a keyboard. Alright, so this is our list, and now let's define a len function, which is supposed to be a Dunder method. Now self again. Now return len self dot products. Alright, now let's understand what's happening here. Inside the class, we're storing products in a regular Python list. Now, when Python calls catalog dot, when Python calls catalog dot double underscore len double underscore, our method simply returns the length of that internal list. Notice that we aren't restricted to using a list. In production systems, developers often calculate lengths from database records or API responses, or files, or even cache entries. The important thing is that the Dunder method len must return an integer. Now, let's see this. Let me remove this. Sorry. Let's create an object, product catalog, and print len catalog. All right. Now let's run this. Let me open my terminal, and let's type python main.py. As you can see, 3 has been printed here. Our custom object now supports len, just like any other native Python list. Now, let's compare the behavior. Without len, how would this function? Now, let me remove this len function, or like comment it out. If I save this and run this again, we get an error. Now, but with len implemented, we would get this. Now, we've taught Python how to measure our object. This is exactly how Dunder methods work. We provide the behavior and Python provides the syntax. Now, let's talk about indexing. Now, when you write, say, catalog and index it, it looks like Python is directly accessing the object, but that's not what's happening here. Behind the scene, Python executes. Let me give an arrow, catalog dot double underscore get item double underscore and passes 0. All right, now that we know that this is what happens behind the scenes, we can say that the index value is passed directly into the Dunder method. So if we define get item, we can control exactly what happens when someone uses square brackets on our objects. Now let's implement this again. Now let me remove this and let me make this smaller. Now let's define, sorry, let me keep this, let me remove this. Let's uncomment the len method, sorry, and let's implement our own get item. Get item double underscore self, and we pass an index for the index to be returned. Now we return self dot products on square brackets, we write index. Now let's test this. Now we already have our catalog object. If we go down and say we go print catalog 0, let me pull this up, let me clear this, and let me type python main.py. We get 3 and we get laptop, which is the first element of this list. Now that's pretty cool. Now our custom object now supports indexing exactly like a Python list, but there's something even more interesting here. Now let's try a loop. Let's try a for loop. Now if we go say for product in catalog, and we simply print product, let's run this, we get all our elements printed. Now notice that we never implemented a loop method. Python automatically uses get item to support iteration. This is one reason why so many professional Python libraries implement this method. Now, you might be wondering where this is actually used in the real world. The answer is everywhere. Pandas data frames support indexing and length operations. NumPy arrays behave like collections because they implement these kind of Dunder methods. PyTorch datasets use len and get item on a regular basis, so training loops can work automatically. Django query sets behave like lists for the same reason. Experienced Python developers often design classes so they feel natural to use. Instead of forcing users to call catalog.getProduct and index 0 again, they can simply write catalog big square brackets in 0 so that it feels more cleaner and natural. Now, this was a quick video, and let's quickly recap what we've learned today. Now, when we write len obj, what's actually being called is obj dot double underscore len double underscore. Now when we write obj square bracket index, we're actually calling get item. Now By implementing these Dunder methods, custom classes can behave like built-in Python collections. This makes APIs cleaner, easier to use, and more intuitive. And it's also a technique used heavily throughout the Python ecosystem. In the next video, we'll continue exploring Dunder methods and learn how operator overloading works using add, or the Dunder function add. We'll see how Python powers expressions like a plus b behind the scenes. If you found this video useful, please make sure to like the video, subscribe to the channel, and leave a comment telling me which Dunder method you'd like to explore next. Thanks for watching, and I'll see you in the next one. Hello everyone, welcome back to the Python OOP series. In the previous videos, we learned about Dunder methods and saw how Python uses special methods like init, str, repr, len, and getitem behind the scenes. Today, we're going to learn another powerful application of Dunder methods, operator overloading. Now, have you ever wondered how Python knows what to do when we write 10 plus 20 or hello plus world? The same plus operator works differently depending on the object type. And the interesting part is, we can teach Python how the plus operator should work for our own classes as well. By the end of this video, you'll understand how operator overloading works, why it exists, and how professional developers use it in financial systems, scientific computing, and mathematical libraries. So let's get started. Now, before we jump into operator overloading, let's quickly recap what we've learned so far. We've learned that Python syntax often maps directly to Dunder methods. For example, len obj calls the Dunder method len, and print obj calls the Dunder method str. Indexing calls getitem. Today, we'll see that operators work exactly the same way. The plus sign isn't magic. It's simply another Dunder method being called behind the scenes. Now, how does a plus b work? Let's have a look at a few examples. When we write 10 plus 20, Python returns 30. When we write hello plus world, Python returns hello world. The same operator is being used, but the behavior is different. For integers, it performs addition, and for strings, it performs concatenation. This should immediately remind you of polymorphism. The same operation can produce different behavior depending on the object receiving it. Now, let's see how Python actually makes this happen. Now, when we write a plus b, Python actually translates that into a dot add, which is a Dunder method, b. That's it. The plus operator is simply a cleaner way of calling the add Dunder method. This means that if we define our own add method, we can decide what the plus operator means for our custom classes. This process is called operator overloading. We're overloading the operator with custom behavior. Python handles the syntax and we define the logic. Now, before writing the code, let's understand why this feature exists. Imagine we're building a financial application. Without operator overloading, we might have to write money1 add money2. Or if we're working with vectors in a machine learning project, vector1 add vector2. This works. It works perfectly fine, but it does not feel natural. With operator overloading, we can write money1 plus money2 or vector1 plus vector2. This reads much more naturally. It feels like working with built-in Python types. That's the goal of operator overloading, to make custom objects behave naturally and intuitively. Now, let's switch to code. Alright, let's implement a money class. So we go class money. We define our constructor as usual. We pass self and we pass an amount. Now, we initialize self.amount is equals to amount. There's an extra dot here. Now we define our custom add Dunder method, self, other, and let's return money self.amount plus other dot amount. Alright, now let's try and understand what's happening here. The constructor stores an amount. The add method receives another money object. Inside the method, we are adding the amounts together. then we're returning a brand new money object. Notice something important. We're not returning an integer, we're returning another money object. This is how professional libraries usually implement operator overloading. The results remain the same type as the original objects. Now let's test this. So let's define two wallets. Wallet 1 is equals to money, and let's initialize wallet 1 with 100, and wallet 2 is equals to money, and let's say 50. Now we define a total variable which shall be the addition of wallet 1 and wallet 2. Alright, now let's print the total amount. Print total dot amount. Alright, now let's run this code. Let me pull my terminal upwards. Let me type python main.py, and we get the correct answer, 150, as expected. Now let's think about what happened here. When Python saw wallet 1 plus wallet 2, it automatically executed, let me show you, wallet 1 dot add Dunder method wallet 2. Now the method created a new money object containing the value 150, and that's what was stored inside the total. This is why operator overloading feels so powerful. The syntax looks so simple, but we control exactly what happens behind the scenes. Now, you might be wondering where this is used. The answer is everywhere. Scientific libraries such as NumPy overload operators for arrays and matrices. Mathematical libraries overload operators for vectors and symbolic expressions. Financial software often overloads operators for currency and monetary calculations. Physics simulations use operator overloading heavily because equations become much more easier to read. Instead of calling long method names repeatedly, developers can simply write expressions that resemble actual mathematics. This makes code cleaner and easier to understand. Now, the plus operator is only one example. Python provides Dunder methods for many different operators. For example, Dunder method sub for minus, Dunder method mul for multiplication, Dunder method trueDiv for dividing, and much more. Now, almost every operator in Python has a corresponding Dunder method. This means you can customize much more than addition. You can customize comparisons, multiplication, division, sorting behavior, and many other operations. This flexibility is one reason why Python is so expressive. Now, let's quickly recap what we've learned today. When you write a plus b, Python calls a Dunder method b. Operator overloading allows us to customize how operators behave for our own classes. It helps create cleaner and more intuitive APIs. It's commonly used in financial applications, scientific computing, mathematical libraries, and many production systems. And just like other Python syntax, it's powered by Dunder methods behind the scene. In the next video, we'll move on to one of the most useful features in Python called decorators. You'll learn how to modify the behavior of functions without changing the function itself. If you found this video useful, make sure to like the video, subscribe to the channel, and leave a comment. Tell me which operator you would overload in your own project. Thanks for watching, and I'll see you in the next one. Hello everyone, and welcome back to the Python OOP series. In the previous videos, we've been exploring Dunder methods and learning how Python allows us to customize the behavior of objects. Today, we're shifting our focus from classes to functions. We're going to learn one of the most important and powerful features in Python, decorators. Decorators allow us to add functionality to existing functions without modifying their source code. This concept is used almost everywhere, and especially in professional software development projects in Python. Logging, authentication, performance monitoring, API routing in FastAPI, and many other important features rely heavily on decorators. By the end of this video, you'll understand what decorators are, why they exist, and how they work under the hood. So let's get started. Now, before we talk about decorators, let's quickly recap. In the previous videos, we learned that Python allows us to customize object behavior through Dunder methods. For example, len calls the Dunder method len. Indexing also calls the Dunder method getitem. And there are multiple other Dunder methods used in Python as well. Those special methods allowed us to customize classes. Today, we'll learn how Python allows us to customize methods or functions. Now, let's imagine we're building a backend application. We have multiple functions: create user, delete user, update user, etc. Let's have a look at this in code. Now, this is exactly the same three functions we had in our presentation. At first glance, everything seems fine, but notice something. Every function contains the logging print or the logging function, which can be implemented later. Now, the same code is repeated in all the three functions. Now, let's say we have 50 functions or 100 functions, or let's say we might even have 500 functions. What happens if we want to change the logging behavior? We'll have to go and update every single function. This kind of repeated functionality is called cross-cutting concern. Now, examples included are logging, authentication, performance monitoring, validation. Decorators were designed to solve exactly this problem. So, what exactly is a decorator? A decorator is a function that takes another function and adds extra behavior to it. The original function remains unchanged. Instead, the decorator wraps it. Think of it like wrapping a gift or a parcel. The gift itself doesn't change. We are simply adding another layer around it. In professional software systems, decorators are commonly used for logging, authentication, authorization, timing, input validation, and API routing. The key idea is very simple: add functionality without modifying existing code. Now, before decorators make sense, we need to understand something important about Python. Functions are first-class objects. This means that functions can be treated like any other object. Let's see an example. Now, we have our three functions. Let's say update user is equals to, no, let's not say update user, let's just say update is equals to update user, or let's just say update user. And now if we go update user, or not update user, update, and if we run this code, let me open my terminal, new terminal, this up, python main.py. As you can see, the update user function has been printed. So what happened here? We assigned a function to a variable, then called it through that variable. This works because functions are also objects, just like strings, integers, lists, dictionaries, etc. This idea is one of the foundations of decorators. Now, since functions are objects, they can also be passed as arguments. Say, we make another function. Let me remove this. Let's say def, and let's just call it a func1. And let's pass update user here. And if we go update user, no, let's not say update user, let's just say func here. And let's just call our func here. Now, in func1, if we pass update user, let's see what happens. Let me clear this. Let me run python main.py again. As you can see, update user has been printed again. Now, notice something important. We passed update user, we just passed update user, not this. We did not pass the parentheses. There's a huge difference. Update user with parentheses executes the function immediately. Update user without the parentheses passes the function object itself. The execute function receives that function and calls it later. This ability to pass functions around is exactly what decorators rely on. Now, let's build an actual decorator. Now, let me remove all of this. Let me pull my terminal down. And let's build a decorator called my decorator for simplicity. And let's pass a function. Now, we will have a wrapper, just like gift wrappers. And let's print saying before execute our function and print after. All right. Now, after this is done, let's go back to the first function and return wrapper. All right, let's break this down. The outer function receives another function as an input. Inside, we create a wrapper function. The wrapper adds behavior before the original function runs. Then it calls the original function, then adds behavior afterwards. Finally, the decorator returns the wrapper function. This is the core structure of almost every decorator you'll ever write. Now, let's see this in action. Let's create a function saying say hello, and let's just print hello ml orbit. All right. Now, let's create our decorated run. Decorated is equals to my decorator, and let's pass say hello without the parentheses, specifically without the parentheses. And now if we call decorated, let's see what happens. Let me open my terminal again, and let's print python main.py. All right, we got before hello orbit, hello ml orbit, and after. Notice what happened here. The wrapper gained control of the execution flow. It executed code before the original function, then it executed the original function, and at last it executed code after the original function. This is why decorators are so useful. They allow us to inject behavior around existing objects or functions. That's how logging decorators, timing decorators, and authentication decorators work in production systems. Now, it is very important to understand the at syntax as well. Manually decorating function works, but Python provides a cleaner syntax. Let's look at a manual version. Now, we have our say hello. We have our function. We have our object as well called decorated. Let's rename this to say hello. And let's remove this. All right. Now let's look at the modern version. Instead of this, what we can do is we can simply call at my decorator and then write our function. So let's remove all this, add our decorator, add my decorator, and then, yeah, so this is it. So these two examples, so this example and the previous example, which was this, is exactly the same. The second version is simply cleaner and easier to understand. It automatically performs what we were executing previously behind the scenes. This is the exact syntax you'll see in real projects and frameworks like FastAPI. Now let's try and run this. Let's call, let's print say hello and see what happens. Yeah, as you can see, before hello ml orbit and after have been printed. Yeah. Now let's quickly recap. Decorators allow us to add functionality to functions without modifying the original code. They solve cross-cutting concerns such as logging, authentication, timing, and validation. Decorators are possible because functions are first-class objects in Python. Functions can be assigned to variables, passed as arguments, and returned from other functions as well. A decorator wraps another function and adds behavior before or after execution. And the add decorator syntax is simply a cleaner way of writing functional reassignment. In the next video, we'll learn how to write production-ready decorators using args, keywords, arguments, function tools, .wraps, etc. We'll also build timer decorators, debug decorators, and retry decorators that are used in real software systems. Now, I know this video is a little hard to understand, but if you found this video useful, make sure to like the video, subscribe to the channel, and let me know if you found anything a little vague or if you need any help. I'll always reply to the comments, and try using decorators on your own. Thank you for watching, and I'll see you in the next one. Hello everyone, and welcome back to the Python OOP series. In the previous video, we learned what decorators are and how they allow us to add functionality to existing functions without modifying the original code. We built our first decorator and learned how the add decorator syntax works behind the scenes. However, our decorator was very simple as we were only using simple functions without any arguments accepted or values returned. So, in this video, we will be learning how professional developers write production-ready decorators. We will be covering args or arguments, keywords or keyword arguments, returning values correctly, functools.wraps, which is very important, and three types of decorators: timer, debug, and retry. These are patterns you'll encounter in real backend systems, FastAPI applications, machine learning pipelines, and production Python code. So let's get started. Now, before we begin, let's quickly recap what we learned in the previous video. We learned that decorators allow us to add functionality to an existing function without modifying the function itself. Conceptually, a decorator sits around a function and enhances its behavior. We can think of the process like this. An original function is wrapped around a decorator to get an enhanced function. We also learned that decorators are possible because functions in Python are first-class objects. This means functions can be assigned to variables, passed as arguments, and returned from other functions. Decorator is simply cleaner syntax for that. Today, we're taking that foundation and turning it into something suitable for production systems. Now, let's switch to code. Alright, so just like in the previous video, we have our wrapper. Before our function is executed, we have before and after. Our function is create user. We have our add decorator syntax here. We have our create user function, and it simply creates a user and prints user created with the name. We've created create user, and we've named our user Dev. So let's run this code. Let's simply type Python, our file's name main.py. We get an error here. So let's break this down. Why does the decorator break immediately? The answer is because the wrapper does not accept any arguments. The original function requires one argument, which is name, and the wrapper simply does not have any. Real production functions almost always have parameters. A decorator that only works on functions without parameters isn't useful in real applications. We need something more flexible. For that, Python gives us a powerful solution. We name them args and keywords. Now, please make sure you are consistent with the syntax, as args consist one asterisk before it, and keywords, which stands for keyword arguments, expects two asterisks before it. Now let's paste this exact same thing here. Now let's understand what's happening. Args captures all positional arguments. For example, here create user Dev is a positional argument. Keywords captures all keyword arguments. For example, if I go create user name is equals to Dev. Now our decorator can handle almost any function signature. Now let's test it. Now let's run this code again. Python main.py. As we can see, we get the expected outcome. Perfect. The decorator no longer cares how many arguments the function accepts. It simply forwards everything to the original function. Now, at this point, many beginners think the decorator is finished. But there's another common mistake. Look at this code. Now, let's decorate a function that returns a value. Let's simply write, let me remove this all. Let me simply make a function called add, let's say, a comma b, and return a plus b. Now, let's result is equals to add 5 comma 10. Alright, now let's print result. Alright, now let's run this code. Let me clear this all. Let me type python main.py again. Sorry. Yeah, so we get before, after, and none. Wait a second. The function should have returned 15. So what happened here? The wrapper executed the function, but it never returned the result. The value disappeared. This bug is surprisingly common in production code. Now, let's fix this problem. Now, we've returned the wrapper here. All we need to do is, okay, so let me remove this, this as well. Let me just write return func args, comma, double asterisk qargs. All right. Now let's see what happens. Let me test again. Let me clear all this. Let me type python main.py. As you can see, we get before 15. Now after is not printed because the function wrapper is already returned after here. So for after is not printed, we can simply remove this. All right, so that's much better. Here's a simple rule experienced developers follow. If the original function returns something, your decorator should return it too. Otherwise, you're silently breaking functionality and creating bugs that are difficult to trace. Now, there's one more issue. Let's look at this example. All right, now let's have a look at the decorators you'll actually encounter in production systems. Timer decorator is the first one. A timer decorator measures execution time. We simply put @timer before our function and we get an output of how much the function was executed for. This is useful for machine learning training, API performance monitoring, and database query optimization. The second one is the debug decorator. A debug decorator automatically logs our function name, the arguments, and the return values. This helps developers trace execution flow without adding dozens of print statements throughout the codebase. Our final decorator for today is a retry decorator. A retry decorator automatically retries failed operations. We simply use @retry and give max attempts as our argument, and the retry decorator runs the attempts for the given number of max attempts entered. This is extremely common when working with external APIs, databases, cloud services, and network requests. Temporary failures in production systems happen all the time, and retry decorators improves reliability significantly. So let's quickly recap what we've learned today. Production decorators should use args and kwargs so that they can work with any function signature. Always return the original function's result, otherwise you'll silently break functionality. Usage of functools.wraps to preserve metadata such as function names and docstrings are highly recommended. And remember that decorators are heavily used in production systems for logging, timing, debugging, authentication, and reliability. Today, you've learned the difference between a simple educational decorator and a production-ready decorator. So, this concludes our decorators section of the Python OOP series. If you found this video useful, make sure to like the video, subscribe to the channel, and leave a comment telling me which decorator you would build first. The next video will probably be on generators. Thank you for supporting the channel, and I'll see you in the next video. Hello everyone, and welcome back to the Python OOP series. In the previous videos, we explored decorators and learned how professional Python developers use them to modify function behavior without changing the actual function code. Today, we're going to learn another powerful feature related to functions called generators. Generators solve a very important problem in software engineering. How do you process massive amounts of data without running out of memory? This is a problem backend engineers, data engineers, and AI engineers deal with all the time. Large log files, massive CSV datasets, machine learning training data, streaming APIs. Generators provide an elegant solution by producing data only when it is needed. By the end of this video, you'll understand what generators are, how the yield keyword works, and why generators are one of the most important tools for building scalable Python applications. So let's get started. Now, before we dive into generators, let's do a quick recap. In the previous videos, we learned about decorators. Decorators allow us to wrap existing functions and add behavior without modifying the original code. We learned that decorators modify function behavior using args and kwargs. And we also learned the very important functools.wraps. Today, we're exploring another powerful function-related feature. Instead of changing how functions behave, we are going to change how functions produce data. Now, let's start with a real-world problem. Imagine you're building a backend service that processes log files. Maybe the log file contains millions of records, or maybe you're training a machine learning model on a huge dataset. A beginner might write something like this. Alright, let's now implement a beginner function called getAllRecords. Now, inside the getAllRecords function, let's initialize a list called records, an empty list, and let's write a for loop till 1,000,000, and let's append inside the list, say record and its index. Alright, now let's return the records list. Alright, now let's understand this function. This function works, but there's a huge problem. This function creates the entire collection in memory before returning it. Now let's test it. Let me run the function here, and let us print the len of the returned variable. Alright, now let me run this code. We get 1,000,000 again. Alright, looks fine, but what happens if the dataset is insanely huge? What if the dataset is of 10 GB but the available RAM is only of 8 GB? Your application could crash with a memory error. The fundamental problem is that we are trying to load everything into memory at once. Real-world datasets often don't fit into memory, so we need a different approach. Now, this is where generators come in. Generators solve this problem beautifully. Instead of creating everything at once, generators produce values one at a time. Now, let's rewrite our example. Say, let me remove this function out. Let me write def get records is our new function, and we write the same loop till 1,000,000. That's 1,000,000, and instead of returning or printing anything, we yield. So remember this yield keyword. We yield the exact same thing. Now here we replaced return with yield. That single keyword changes everything. Instead of building one giant list, the function produces records only when someone asks for them. This means we never need to store all 1,000,000 records in memory. Generators generate data only when it's needed. That's why they're incredibly memory efficient. Now, let's understand the most important concept. What's the difference between return and yield? Let's consider this function. Let me remove all of this. Now, let's say a normal function would have return, say, let's type return 1, and let's have another return inside the same function 2. Alright. The moment Python encounters return inside the function ends. Execution of the function stops. The function state disappears. Now, in yield, now let's write a generator function. I need a colon here. Generator function. Let's yield 1, yield 2, yield 3. Alright. Now, when Python encounters yield, something different happens. Instead of ending the function, execution is paused, state is preserved, the value is returned. For example, here the value is returned, and the function can resume later. Think of yield as a checkpoint. The function pauses and remembers exactly where it stopped. The next time we request a value, function executes from the exact same point. For example, if yield 1 is called, and the next time the function is called, we start from here. Alright, now let's get towards generator objects. Let's see what happens when we call a generator. We have our generator function. Let's say we initialize a G called our function is generator function, and let's print type G. Alright, let's run this code again. We get class generator. Interesting. The function didn't execute. We didn't see 1, 2, or 3. Instead, Python created a generator object. This is very important. Calling a generator function does not execute its code immediately. It creates a generator object that is waiting to be consumed. Execution begins only when we request values from it. So, how do we request values from it? We request values from it using the next keyword. Now, we have our G, which is a generator object. Now, instead of printing type here, let's just replace this with next. Let me run the function again, and we get 1. Now, let me run the function again. We get 1 again. Now, if I print next G here, what happens if I run the function again? I apologize. We get 1 and 2. Now, what if I print a third next here? We will get 1, 2, and 3. What happens internally? The first call, which is the first next G, starts the execution. Python run until it encounters yield 1. Then execution pauses. The second call resumes execution after the first yield. Python continues until yield 2, and then it is paused again. The same process repeats for every yield statement. Now, let's see what happens if we ask for another value. Say, let's return this again. Now, let me clear this and let me run the function again. Alright. Here we get stop iteration. This exception tells us the generator has finished producing values. This is how Python knows when iteration is complete. Now, let's have a look at something else. And let's see where generators become really interesting. Let me remove all this. Let's write def count, which is our new function. Give n is equals to 1. Let's have a while loop, less than or equal to 3. Let's type yield n plus is equals to 1. Alright, a simple function. Now let's test it. Let me clear this. And let me create a variable called counter count. Now let's print next counter, and let's print this 2 more times. Alright, now let's run this code. Python main.py. We get 1, 2, 3. Notice something remarkable. The variable n keeps its values between calls. Python remembers local variables, current execution position, and function state. The function doesn't restart every single time. It resumes exactly where it left off. This is the core magic behind generators. Now, let's have a look where generators are actually used. Now, truth be told, the answer is everywhere. Backend systems, generators are commonly used for processing huge log files, reading large CSV datasets, streaming JSON data, API response pipelines, etc. Instead of loading gigabytes into memory, data is processed one record at a time. In AI and machine learning, this is especially important for AI systems. Now, imagine training a model on millions and millions of images. We can't load the entire dataset into RAM. Instead, generators yield small batches of data. Frameworks like TensorFlow and PyTorch rely heavily on generator-like concepts for efficient data loading. Many AI training pipelines would be impossible without this technique. Now, let's quickly recap what we've learned today. A function containing yield becomes a generator function. Calling a generator function does not execute it immediately. Instead, it creates a generator object. Generators are lazy. They produce values only when requested. The yield keyword pauses execution rather than ending it. Generators are known to preserve local variables, execution state, and current position. This makes them incredibly memory efficient compared to lists. And that is why generators are used widely in backend systems, data preprocessing pipelines, and AI workloads. Now, in the next video, we'll build on this foundation and learn about generator expressions, data pipelines, list comprehensions versus generators, and TensorFlow and PyTorch data loading patterns. If you found this video useful, please make sure to like the video, subscribe to the channel, and leave a comment telling me where you think generators could help in a real project. Now, thanks for watching, and I'll see you in the next one. Hello everyone, and welcome back to the Python OOP series. In the previous video, we learned about generators and how they allow us to process massive amounts of data without loading everything into memory at once. We learned that the yield keyword transforms a function into a generator, allowing it to pause and resume execution while preserving its state. Today, we're going to take that idea further. We're going to learn generator expressions, lazy evaluation, memory efficient processing, data pipelines, and how AI and backend systems process enormous datasets. This is where generators become genuinely useful in real-world software engineering. By the end of this video, you'll understand why frameworks like PyTorch and TensorFlow rely heavily on these concepts. So let's get started. Now, before we dive into today's topic, let's do a quick recap. In the previous lesson, we learned that generators are used using the yield keyword. They produce values on demand, they preserve execution state, and they use very little memory. We also learned that a generator only computes values when they are requested. Today, we're going to make generators even more powerful by learning generator expressions and data pipelines. Let's get started with generator expressions. If you've ever used a list comprehension, this syntax will look familiar. Alright, so we've switched to code. Let's start by typing squares is equals to, let's name our variable x squared for x in range, let's say 5. Now, let's print squares. Sorry, variable naming error, squares. Alright, now let me open my terminal, new terminal, and let me type python main main.py. Alright, so we get the output. This is a list comprehension. Python immediately calculates every value and stores the complete list in memory. Now, let's create a generator expression. Say, instead of square brackets, let's use the round brackets, and let's build again. Alright, we get the generator object. Interesting. Now, instead of a list, Python here has given us a generator object. The only difference was square brackets for the round brackets. But the small syntax change completely changes how Python handles memory. The list computes everything immediately. The generator computes values only when requested. Now, let's see why generator expressions exist. Imagine we are processing 1 million values. Let me remove all this. Let's type numbers list is equals to, let's use x again, in range 1 million. Yes, that's 1 million. Alright, now let's print type numbers list. Let me clear this and let me run python main.py again. We get output class list. This creates 1 million integers immediately. Now, if we run a generator expression by removing the square brackets and using the round brackets, if we run, we get class generator. The difference is enormous. The list stores 1 million values in memory. The generator stores only the current position, the execution state, and the iterator information. The memory usage stays almost constant regardless of the dataset size. This is why generators are essentially a lazy list, and they are essential for scalable systems. Now, the key concept behind generators is lazy evaluation. Nothing happens until we ask for data. Let's try and see that in action. Let's use this. Let me remove this. Just type 5, and whenever we print this, we get class generator. At this point, no squares have been, or nothing's been calculated here. Let me calculate squares here. At this point, no squares have been calculated. We've only created sort of a recipe. Now, if we request values, say print next and type numbers list. Let me clear this again. Let me python main.py. We get 0. This is for this print and 0 is for this print. Now let me comment this out for a clearer evaluation. Let me copy this and let me print this 4 times. All right, this is the same code. Let me run this again. We get 0, 1, 4, and 9. All right, notice what happened. Each call to next computed exactly 1 value, not 2, not 5, exactly 1. This is lazy evaluation. Work happens only when needed. This makes generators incredibly efficient for large-scale processing. Now, let's talk about data pipelines. This is where generators become extremely powerful. Imagine processing a CSV file. You might need to read the file, remove invalid rows, convert data types, and produce results. A beginner might store the output of each step in a separate list. This would waste memory. Instead, generators allow us to chain operations together. Conceptually, raw data, then to filter, then we transform, and then we get the output. Each state processes one item at a time. No massive intermediate lists are created. Now, let's switch to code again. Now, let me remove all this. Now, let's write a function def read data. Now, in this function, we shall create a data. Now, let's say we put 1, 2, 3 together, create a comma, and empty, sorry, not capitalize. Now, 4, 5, 6 together, comma, again empty, and again 7, 8, 9 together. All right, I'm sorry, I used the wrong brackets here. Now let me remove the excess bracket. All right, now in the same function, let me add a for loop for row in data. Say yield, we're using the yield keyword row. All right, now this is our simple pipeline. Let's create a filter stage. Now let's skip the empty ones. That's our filter. Now we add rows here. For row in rows, if row, we yield row. This would mean if row is not present, we would not yield row. All right, now we'll transform the data. Say, or let's define, let me close this terminal for now. Let's define another function called parse ints. So def parse ints. Let's pass rows again. Now again, let's write a for loop for row in rows. Yield. Now this is very important. Let's create a list. Now we go int x for x in row dot split, and we split using a comma. All right, now let's try and chain everything together. Let's type pipeline. So
for our pipeline. We go parse ins, and inside parse ins, we pass skip empty, and inside skip empty, we pass read data. All right, now let's go for row in pipeline. Let's print our row. All right, now let's run the code. New terminal. Let's go python main.py. We get 1, 2, 3, 4, 5, 6, 7, 8, 9. Now notice something important. Data flowed through the 3 processing steps, but at no point did we load everything into the memory. So there's no loading everything into the memory. Each row moved through the pipeline one item at a time. So this is quite important. All right, now let's understand something more important. Let's understand why this architecture scales so well. Most people imagine data being pushed through a pipeline, but generators actually work the opposite way. The final stage requests data. The request moves backward through the pipeline. For example, the consumer asks for a value. The transform stage requests data, then the filter stage requests data, then the reader loads one record. Only one record moves through the system. This approach is called a pull-based execution. I want you to remember that, a pull-based execution, because data is only generated when someone requests it. This minimizes memory usage and prevents unnecessary work. So this concept is incredibly important in machine learning. Imagine training a neural network. The data set might contain millions and millions of images or audio files or terabytes of text. We cannot load all of that into the memory. Instead, frameworks use generator-style processing. For example, PyTorch data loaders. I hope you're familiar with them. If not, I'll be making a PyTorch series as well. So PyTorch data loaders generate many batches on demand. TensorFlow datasets as well stream records through processing pipelines, and many AI systems continuously generate batches while training is happening. A common pattern looks like this. It looks like def, let's say data generator. This is our function. While true, we yield a batch of data. So this is what a common pipeline looks like. The model requests data. The generator provides the next batch. The memory usage remains low no matter how large the data set becomes. And this is one of the reasons generators are so important in AI engineering. Now let's quickly recap. Generator expressions provide a compact way to create generators. Instead of using a list, we can using a square bracket, we use rounded brackets to use generators. Generators use lazy evaluation. Values are computed only when needed. Generator pipelines allow us to process data through multiple stages without creating large intermediate collections. This pattern is widely used in backend systems, data engineering, AI pipelines, and frameworks like PyTorch and TensorFlow. So this was it for this video. In the next video, we'll begin exploring context managers and the with statement. We'll learn how Python automatically manages resources and prevents issues like file handle leaks, etc. If you found this video useful, make sure to like the video, subscribe to the channel, and leave a comment telling me where you would use generator pipelines. Thanks for watching, and I'll see you in the next one. Hello everyone, and welcome back to the Python OOP series. In the previous video, we learned about generator expressions and data pipelines. We saw how Python can process massive amounts of data efficiently by generating values only when they're needed. Today, we're going to solve a different problem. A problem that affects almost every real-world Python application. How do we make sure resources are always cleaned up properly? Files need to be closed once they're opened. Database connections need to be released. Network sockets need to be terminated. Locks need to be unlocked. If we forget to clean up these resources, our applications can leak memory, exhaust system resources, or behave unpredictably. This is exactly why Python provides context managers. By the end of this video, you'll understand the with statement, the the content manager lifecycle, and why experienced engineers use context managers everywhere in production code. So let's get started. Now, before we begin, let's quickly recap. In the previous video, we learned about generator expressions, lazy evaluation, data pipelines, and memory efficient processing. We saw how data could flow through multiple processing stages without creating large intermediate collections. Today, we're shifting our focus from managing data efficiently to managing resources safely. Let's start with a very common example by switching to code. Right, imagine we're writing data to a file. Let's type f is equals to open. Let's name our file data.txt and let's write. Now, let's go f.write, say hello ml orbit. Alright, now f.close is to be written. This looks perfectly fine. We write some data and we close the file. Here we are opening the data. We write some text to the file and then we close the file. But let's imagine something goes wrong. Say we raise an exception here. Raise exception. Something is wrong. Alright. Now let's run this code. So let me open my terminal. Let me type python main.py. We get exception, something is wrong. Alright. The program crashed before reaching f.close. This means that the file never got closed. This is called a resource leak. In small programs, it might not seem that serious. However, in production systems, leaking file handles, database connections, or network sockets can eventually bring an application down. That is why engineers never rely on manually calling cleanup methods. Now, context managers are obviously the solution to this problem. However, before context managers existed, the standard solution was the famous try finally. Let's see how that works. So now let me put a try block here. Let me indent. And let's say finally and indent. All right. Now let's run this again. Here, the output is the same. Even though the exception occurred, the file was still closed. Why? Because finally block is always executed. Does not matter whether the code succeeds, an exception occurs, or a return statement executes. The finally block is always run. This guarantees cleanup. The problem is that this pattern becomes very repetitive. Imagine writing this around every file, database connection, API session, and lock in a large code base. It quickly becomes very noisy and difficult to maintain. Now, Python provides a cleaner solution, the with statement. Now, instead of writing all this, let me simply remove this. We type with open as usual. Then we type data.txt with w as f. Alright, now we write f.write, say hello ml orbit. Let's see what our data.txt looks like. It looks like hello ml orbit. Now let me just type 2 here. Now let's run this code. Let me clear this first. Python main.py. Sorry. We get no error or exceptions, and hello ml orbit 2 is written to the txt file. Now, when execution leaves the with block, Python automatically closes the file, even if an exception occurs. Let's have a look at this by raising an exception. Exception. Something is wrong again. All right. Now let me run again. We do get an error or an exception, but Python automatically performs cleanup. the file is closed for us. That's the main purpose of context managers, automatic resource management. Alright, it is essential to understand the context manager lifecycle. Every context manager follows the same lifecycle. Python enters the context. The code inside the with block is executed. Then Python exits the context and performs cleanup. Internally, this process is controlled by two special methods, enter and exit. Both are Dunder methods. If you've not understood Dunder methods, go back to our Dunder methods videos. We can think of this cycle like this. Enter is a setup, execute block is us using the resources, and exit is simply cleanup. This structure appears throughout the Python ecosystem. Files, databases, connections, locks, network sessions, they all follow the same pattern. Now, let's look under the hood by switching to code again. Let's remove all this. Now, when we write with resource as R, we go do work. This is just an example. Python is effectively doing something similar to this. Say R is equals to resource dot Dunder method enter. Then a try block executes do work, and we have a finally block with resource dot Dunder method exit. So this is essentially what happens. The with statement is a syntax sugar per se. It hides the repetitive setup and cleanup code. This is why context managers feel so elegant. The logic remains exactly the same, but the code simply becomes cleaner and it's easier to read. Another interesting detail is that the exit Dunder method receives exception information if an error occurs inside the block. This allows context managers to react to failures and perform intelligent cleanups. Now, where do engineers actually use context managers? The answer is almost everywhere. The most common example is with.open for files, for database connections, where automatically we can commit, rollback, and close connections, network sockets, where we ensure connections are released correctly, thread locks, which automatically acquires and releases locks, and API sessions. Libraries like requests use context managers to manage HTTP sessions and connection pools efficiently. Anytime a resource requires setup and cleanup, context managers are usually the preferred solution. Now, why do engineers love them? At the very first glance, context managers seem like a small feature, but they solve several major problems. First, automatic cleanup. There's no more forgotten close calls. The second problem they solve is fewer bugs. Resource leaks become much less likely. The third is less boilerplate. 5 or 6 lines of cleanup logic become a single with block. And finally, improved readability. When another developer sees with database connection or with data or with open file, they immediately understand the setup and cleanup are being handled automatically. That's one reason context managers are considered a best practice in professional Python code. Now, let's do a quick recap. Context managers automate resource management. The with statement provides a clean way to guarantee cleanup. Behind the scenes, every context manager relies on the enter Dunder method and the exit Dunder method. These methods handle setup and teardown automatically. Context managers help prevent resource leaks, forgotten cleanup, repetitive boilerplate code, etc. And they're used extensively in file handling, database systems, networking, concurrency, and backend applications. Now, in the next video, we'll go one step further. Instead of just using context managers, we'll build a context manager of our own. We'll be implementing the enter and exit Dunder methods and inside custom classes and learn how professional developers create context managers for real-world systems. Now, if you found this video useful, make sure to like the video, subscribe to the channel, and leave a comment telling me where you've used the with statement before. Thanks for watching, and I'll see you in the next one.
Hello everyone.
and welcome back to the Python OOP series. In the previous video, we learned what context managers are and how the with statement automatically handles resource cleanup. We saw that context managers help prevent resource leaks by guaranteeing that resources are released even when exceptions occur. But so far, we've only used context managers. Today, we're going to build our own. You'll learn exactly how Python's with statement works behind the scenes by implementing the two special methods that power every context manager, the enter Dunder method and the exit Dunder method. By the end of this video, you'll be able to create your own context managers for databases, API clients, file processing systems, and many other real-world applications. So let's get started. Now, before we begin, let's do a quick recap. In the previous lesson, we learned that context managers automate cleanup. The with statement prevents resource leaks. Python automatically handles setup and teardown, and the process relies on two Dunder methods, enter and exit. Today, we're going to go on a deeper level. Instead of using context managers, we're going to build them ourselves. Now, many beginners think context managers are some special Python feature, but they're actually much simpler than that. A context manager is just a normal Python class that follows a specific contract. Let's build one. Alright, now we're back in VS Code. Let's implement a database connection class. So we write database connection. We define our enter Dunder method, and let's print. Let me fix the indentation. Let's print opening connection and return self. Alright, now let me write the exit Dunder method, remove pass. Now here we have, along with self, three added parameters passed. This is exception type, this is exception, and this is traceback. Alright, now let's not implement anything here. Let's just print closing connection. Alright, now at first glance, this looks like a regular class. The only difference is the presence of two special methods, the enter Dunder method and the exit Dunder method. These methods tell Python how to manage the resource lifecycle. There is no magic, there's no special inheritance of any kind, just a class following a convention. Now let's focus on the first method, the enter method. We have print opening connection and return self. The purpose of enter is to perform setup. In a real application, this might mean opening a database connection or opening a file, creating an API session, or even acquiring a thread lock. Notice that we are returning self. Why? Because the value returned from enter becomes the variable after the as keyword. For example, let's say we have with database connection again as db, or rather, yeah. Now the variable db receives whatever the enter returns. That is why returning the resource is a common pattern. Another important detail, enter always runs before the code inside the with block. Now let's look at the cleanup phase. We have the exit Dunder method. This method performs cleanup. In a real application, it might close a database connection or close a file. It might also release a lock and disconnect a network socket. You may have noticed these three parameters, exe type, exe, and tb. These contain exception information. If no exception occurred, none is passed. If an exception did occur, Python provides details about what went wrong. This allows advanced context managers to react intelligently to failures. Now, let's actually use it. This is fine. Here, we shall be writing print running queries. Now, if we run this code, let me open my terminal, new terminal. Let's type python main.py. We get our three outputs. Now let's break down what happened. On the very first step, Python creates the object. In the second step, Python calls the enter Dunder method. The third step, the code inside the with block is executed. And in the fourth step, the exit Dunder method is called, hence printing closing connection. All of this happens automatically. That's the beauty of context managers. Now, let's test the most important feature. What happens when something goes wrong? Now, let's raise an exception instead of this print. Let me remove this completely. Let me raise an exception saying, let's just say database error, considering we're using a database example. All right, let's use an exclamation mark as well. Now, let's run this code again. Let me clear the entire terminal. Now, here, we get an exception saying database error. Even though an exception occurred, Python still called the exit Dunder method, meaning cleanup happened successfully. This results in no resource leak. This is exactly why context managers are trusted in production systems. They guarantee cleanup regardless of whether code succeeds or fails. Now, where are custom context managers used in real software? The answer is almost everywhere. Database connections, using with database connection, just like in our example. We open the connection, run queries, and close the connection automatically. For API sessions, we use similarly with API session. Here we manage authentication and network resources. We use them for file processing as well. We simply write with open and open our file. Now, this is Python's most common built-in context manager. And finally, we use them for thread locks. We acquire and release locks safely. In production systems, engineers constantly manage resources. Context managers make the process safe and reusable. Now, at the first glance, context managers seem like a small feature, but they solve several major engineering problems. First, automatic cleanup. No more forgotten close calls. Second, exception safety. Resources are released even when the code crashes. Third, reusable logic. You write setup and cleanup code once and use it or reuse it everywhere. Finally, we have less boilerplate, meaning cleaner code. Instead of repeatedly writing try finally, you write a simple with block. This improves readability and reduces bugs throughout a code base. Now, let's quickly recap. Context managers are simply classes that implement the enter and exit Dunder methods. The enter Dunder method performs setup and the exit Dunder method performs cleanup. Python automatically calls both methods when using a with statement. Most importantly, the exit Dunder method runs even in a exception case or even when an exception occurs. That's why context managers are considered a production grade resource management pattern. You'll find them everywhere, from databases to APIs, file locks, backend systems, etc. Now, in the next video, we'll learn a more Pythonic way to create context managers using the context manager decorator from the context lib module. We'll combine generators and context managers to create elegant resource management solutions with far less code. Now, if you found this video useful, make sure to like the video, subscribe to the channel, and leave a comment telling me what kind of context manager you would build. Thank you for watching, and I'll see you in the next one. Hello everyone, and welcome back to the Python OOP series. In the previous video, we learned how to build our own context managers using the enter and exit Dunder methods. We saw how Python uses these special methods to automatically manage resources and guarantee cleanup. While that approach is powerful, there's a problem. For simple resource management tasks, writing an entire class can feel like an overkill. Sometimes all we need is setup code, resource usage, and cleanup code. And writing a full class for that becomes repetitive. That is why Python provides the context lib module. Today, we'll learn how to create context managers using ordinary functions and generators. We'll explore the context lib module, the context manager decorator, generator-based context managers, exception handling, real-world database and API examples as well.
By the end of this video, you'll understand the modern Pythonic way of creating context managers. So let's get started. Now, before we dive into context lib, let's do a quick recap of what we already know. In the previous videos, we learned context managers automate setup and cleanup. The with statement manages resources safely. The enter Dunder method handles setup and the exit Dunder method handles cleanup. We also built custom context managers using class. While that works well, it's not always the most concise solution. Today, we'll see how Python simplifies the entire process. Now let's revisit a class-based context manager. Now this is our example from the previous video. At first glance, this again is not bad, but imagine writing dozens of context managers like this. Every single one requires a class, an enter Dunder method, and an exit Dunder method, even when the logic is quite simple. The actual business logic in production systems might only be of a few lines. The rest is just boilerplate. Now, experienced Python developers prefer solutions that reduce repetitive code while remaining safe and readable. That is where context lib comes in. Now, Python provides a built-in module called context lib. Its purpose is extremely simple. It helps developers create context managers more easily. Let's import it. So we import context lib using from context lib import context manager. Alright, the most important tool inside this module is the context manager decorator. This decorator allows us to turn a generator function into a context manager. There is no custom class required and no Dunder methods required, just a function and a yield statement. Now, it is important to understand that when we use a yield statement, it becomes a generator. So we will be implementing generator-based context managers using the context manager decorator. So let's try and build our first generator-based context manager. Let me remove all this. Now, first we will be writing the decorator context manager line. Then let's just name our function myResource. We do this, and let's just write print for setup. Then we yield the resource, and we print cleanup. So notice something interesting. Now this is just an example. Everything before yield acts like Dunder method enter, and everything after yield acts like Dunder method exit. The yield statement separates setup from cleanup. Now let's use it. Now let me remove all of this, and let's just write. No, let's not remove all of this. Let's go with my resource as resource. Let me add parentheses. Let's print resource. All right. Now let's run this code. Let me open my terminal and type Python main.py. All right. So the output is setup, resource, and cleanup. That's a complete context manager. No class is required, and we're just using a generator function. Now, let's understand what actually happens and how it works under the hood. When Python encounters the with statement, it performs several steps automatically. The function starts executing for the first step. The second step, execution continues until yield. And in the third step, the yielded value becomes the variable. Now, we also have three other steps. The fourth step is the code inside the with block is executed. The fifth step is when the block ends, Python resumes the generator. And the final step, the sixth step, is everything after yield runs. That's where cleanup happens. We can think of the lifecycle like this. So setup, then we go to yield, then we run the block, and then we clean up. This is why generators and context managers fit together so naturally. Now, let's build something more realistic. Imagine a database connection.
Let's make some modifications to this function. Let me just rename this as database connection. All right. Now, here, let's just say we are opening a DB connection. Now, let's implement a try finally block. Let me remove this. Let's say try yield DB connection, and finally let's just say we will be printing DB connection closed. All right. Now here, let's use it. Let me simply remove this for DB database connection, sorry, and let me rename this as con for connect. Now let me remove this as well. All right, now this is the entire function. I'll let you have a look. This is the entire function. You may pause and run it on your own, but we'll be running it immediately. Let me clear the terminal. Clear, and let's run the code. Now here the output is opening database connection, using DB connection, and closing database connection. This pattern appears constantly in production systems: opening a resource, using the resource, and automatically cleaning up the resource. The developer does not need to remember to call the .close manually. Now, one of the biggest advantages of context managers is reliability. Let's see what happens when an exception occurs. Now, let's say here we raise exception, and let's say DB error with an exclamation mark. Now, let's run this. Let me clear it once again. Now we get an exception, but as you can see, the DB connection is closed. Notice what happened. The exception occurred, but the cleanup still happened. The connection was closed before the program terminated. That is because the cleanup code was placed inside the finally block. This is one of the reasons context managers are trusted in production systems. Cleanup is guaranteed. Now, where is context lib used in practice? Simply everywhere. For database sessions, using simply with DB session or any other use case, we can open, use, and close database connections safely. For API clients, we can manage HTTP sessions and connection pools. For file processing, we can use custom file handlers often, and these custom file handlers often use generator-based context managers. We use them for testing. Testing frameworks create temporary resources and automatically clean them up after tests finish. The pattern is always the same: setup, use, and cleanup. Now, context lib simply makes that pattern easier to write and maintain. Now, let's do a quick recap. The context lib module helps us create context managers without writing full classes. The context manager decorator converts a generator function into a context manager. Everything before yield acts as setup, and everything after yield acts as cleanup. Using this approach gives us less boilerplate and cleaner code, automatic cleanup, and production-ready resource management. This technique is used throughout modern Python applications for databases, APIs, files, testing frameworks, and many other systems. That concludes our context manager section of the series. If you found this video useful, make sure to like the video, subscribe to the channel, and leave a comment telling me whether you prefer class-based or generator-based context managers. Thank you for watching, and I'll see you in the next one. Hello everyone, and welcome back to the Python OOP series. In the previous videos, we explored context managers and learned how Python automatically manages resources using the with statement. We also learned how to build our own context managers and how the context lib module simplifies the entire process. Today, we're moving into another topic that's heavily used in professional Python development: type hints. If you've ever looked at modern Python code bases like FastAPI, Django, or any other production backend service, you've probably seen functions that have arrows and their types defined. At first glance, it might seem like Python is becoming a statically typed language, but that's not the case. Type hints are optional annotations that help developers, IDEs, and analysis tools understand your code better. By the end of this video, you'll understand what type hints are, why they exist, and why almost every professional Python team uses them. So let's get started. Now, before we begin, let's quickly recap. Recently, we've covered context managers, custom context managers, and the very important context lib library. All of these topics focused on writing cleaner and safer Python code. Type hints continue that same theme. They help us write code that is easier to understand, maintain, and debug. Now, what is the problem with dynamic typing? Python is a dynamically typed language. That means variables can change types at runtime. Let's see a simple example. Alright, so let's implement an add function saying def add. And let's pass a and b. Now we shall be returning a plus b. Simple, right? Now let's print add, let's say 10, 5. Alright. Now let me open my terminal, new terminal, and let me type Python main.py as usual. We get 15. Everything works. Now let's make a mistake in purpose. Now instead of 5, let's type in ml orbit. Now let's run this again. We get an error. The problem is that Python didn't warn us beforehand. The error only appeared when the code actually ran. In small programs, that's manageable, but in large applications with thousands of functions, these mistakes can become expensive to find and fix. That is one reason type hints were introduced. Now, type hints are annotations that describe the expected type of a variable or a function. Let's have a look at a few examples. Now let me remove this terminal. Let me remove all this. Now name is an str. Say the name is Dev. Age is an int or an integer. Say 23. Price can be a float data type. Say 19.99. Or is active can be of a Boolean data type, which can be true or false. Let's keep it true for now. Notice the syntax. We have variable name and type. The annotation tells readers what kind of value is expected. It also helps IDEs provide better autocomplete and warnings. Most importantly, it makes your intentions clear to other developers reading the code. Now, type hints become even more useful with functions. Now let's remove all this again. Now let's implement a greet function. We pass name, we give our type hint, and we give an arrow with a dash and a greater than or a smaller than sign, and then we type what value is expected. Now we return, say hello, and let's use our name as well. Hello, name. All right. Now let's break this down. Name :str means the parameter should be a string, and arrow str would mean the function returns a string. Let's test it. Now let's print greet and Dev. All right. Now let me open a new terminal. Let me type Python main.py as usual. We'll get hello Dev. Now anyone reading the function immediately understands its contract. That's a huge benefit in larger code bases. Now say, let's try sending 5. We realize that 5 is also hello 5 is also printed. However, developers and other people reading the code would understand that the function expects a string parameter. Now let's compare two versions of a function. let me remove all this. First, let's write process user function. Let's pass data. Let's pass name, data, and let's just say name and age, data, age, or we need. Now let's return name times age. All right. Looking at this function raises several questions. What is data? What does the function return? What type should age be? What type should name be? The answers aren't obvious. Now let's improve this function. Now, data from this syntax we assume is a dictionary. Is a dictionary. All right. Now, name should be a string. Age should be an integer. And from here, we assume that we shall be returning str or string. Now, even before reading the implementation, we can now understand the input type, variable types, and the return type. The function becomes self-documenting. That is one of the biggest advantages of type hints. Alright, again, the most important concept that we'll be learning in today's lesson is that type hints are not an enforcement. They do not enforce types. Let's prove it. Now, I already did this previously in the video to give you a gist, but let's implement a name variable and we type hint string, but we assign an integer. Now let's go print name. Now let's try and run this code. Python main.py. We get 1, 2, 3. Now, why didn't Python complain? Because Python ignores type hints at runtime. They're annotations, not restrictions. The interpreter doesn't enforce them. Instead, type hints are primarily used by developers, IDEs, static analysis tools, etc. We'll talk about one of those tools called MyPy in the next video. Now, let's have a look at a real world example. Now, let me remove all this. Let me implement a function called create user, and let's type hint every single parameter that is to be passed here. So username is obviously a string, age is usually an int, email shall be a string, and let's keep it small for now, and it returns bool. Why? So that we know if the user has been created or not. Now return true. Now the API client has something like a fetch user function, fetch user, and we shall have a user ID which shall be an integer, and considering the user has username, age, and email, this returns a dictionary. Now, what we can do is we can simply just return an empty dictionary. These annotations help developers understand the expected inputs and outputs immediately. Frameworks like FastAPI, Django, and modern backend services use type hints extensively. In some frameworks, type hints even help generate API documentation automatically. So why do professional teams invest time in writing type hints? First, self-documenting code. The code explains itself. Second, there are fewer bugs. Tools can identify type mistakes before deployment. Third, easier onboarding. New developers understand the code base faster and better. And finally, better code reviews. Reviewers can identify issues more quickly when function contracts are explicit. These benefits become increasingly important as our project grows larger. Now, let's do a quick recap of this video. Type hints improve readability. They communicate intent clearly. They help IDEs provide smarter suggestions and warnings. They make large code bases easier to maintain. But remember, type hints do not enforce types. Python still runs normally. Enforcement requires additional tools such as MyPy, which we'll be covering in the next lesson. Now, as I said, in the next video, we'll learn how MyPy performs static type checking and catches bugs before your code ever runs. If you found this video useful, make sure to like the video, subscribe to the channel, and leave a comment telling me whether you've used type hints before. Thanks for watching, and I'll see you in the next one.
Hello everyone, and welcome back to the Python OOP series. In the previous video, we learned about type hints and how they make Python code easier to read, understand, and maintain. We also learned something important. Python does not enforce type hints. You can annotate a function with int integer, str string, or any other type, and Python will happily run your code regardless. So that raises an obvious question. If Python ignores type hints, how do professional teams actually use them to prevent bugs? The answer is a tool called MyPy. MyPy is a static type checker that reads your type hints and finds type-related mistakes before your code even runs. In this video, we'll learn what MyPy is, how to install it, how to use it, and why it's become a standard tool in modern Python development. So let's get started. Now, before we learn MyPy, let's quickly recap what we learned in the previous lesson. Type hints improve readability. They make functions self-documenting and easier to understand. We also learned that Python does not enforce type hints. The interpreter completely ignores them at runtime. That means type hints alone are mostly just documentation. To actually verify whether those type hints are being used correctly, we need a tool that can analyze our code. That is where MyPy comes in. Now, let's look at a simple example through code. Alright, so we're at code. Let's implement our add function. And b is also an int. So we have two variables, a and b. And this obviously returns an integer. Now, say we have return a plus b. Alright, sorry. I made an error here. Alright. Now we have our simple function. Now, say we do result is equals to add. We call the function 5, ml orbit. Now, this should not be possible. We print the result. Now, let's run the code using Python main.py. And as you can see, we get an unsupported operand type s for plus, integer, and string. So this is an integer and this is a string. This is a string, sorry. The problem is not that the code failed. The problem is when it failed. Python allowed us to write the code. Python allows us to save this file. The error only appeared when that specific line was executed. In a large application, the code path might not be triggered until days or weeks after deployment. That's why runtime only checking is risky. We want to catch mistakes before users ever see them. Now, MyPy is a static type checker. The word static means it analyzes your code without running it. Instead of executing your program, MyPy reads the function definitions, type hints, variable annotations, and function calls. It checks whether everything is being used correctly or not. For example, in our previous example, when we defined a function add, MyPy understands that both arguments should be integers. When it sees add 5, hello, it immediately recognizes that something is wrong. This allows developers to find bugs during development instead of discovering them in production. Now, let's install MyPy. Alright, now before installing MyPy, we need to make a virtual environment such that our Python installations are isolated to a specific virtual environment. Now, there are two main ways to make our virtual environment. Well, there are more, but for local development, we can either use UV or pip. Now, here we will be using UV. It's a more advanced and newer way of managing Python versions and Python libraries. Pip only installs Python packages. However, UV is a faster all-in-one tool. It can install and manage Python versions better.
and create virtual environments. So to use UV, will go UV, VNV, and name our virtual environment v.vnv. Now, let's go yes. All right, we have our virtual environment here. Now, what we can do is write this exact command, source vnv slash bin slash activate. All right, our virtual environment is activated. Now, we need to install MyPy. So for that, what we can use is uv and pip install MyPy. As you can see, the download is taking place. This should take a while. Now, as this is installed, let's make a new file app.py. And let's implement our function as needed. All right, but before implementing the function, let me clear all this and let me run mypy app.py. Now this executes our app.py file and it says success, no issues found in one source file. If your file contains no type violations, this is printed. Notice something important. MyPy never executes your program. It only analyzes the code. That makes it fast and safe. That is why static analysis tools are commonly integrated into development workflows and CI/CD pipelines. Now, let's create a real error. Let's implement our add function again. Now, let's run this exact same issue. As you can see, there's an error. It says app.py5 argument 2 to add has incompatible type string expected integer. This is the key benefit of MyPy. The bug was detected before running the application. Let's compare the two approaches. Without MyPy, the code runs, error appears at runtime. With MyPy, error detected immediately and no runtime surprises. That's exactly why teams invest in static analysis. Now, MyPy also provides a stricter checking mode. Let's run MyPy --strict app.py. Alright. Now, strict mode performs additional checks. Examples include missing type hints, missing return annotations, untyped function calls, incomplete type coverage. For example, let me comment this out, or let me just remove this. Let's create a create user function, pass name and return name. All right, this is a simple function. In normal mode, this will definitely pass. However, in strict mode, MyPy will complain that type information is missing. Professional teams often use strict mode because it encourages consistency throughout the codebase. The more information MyPy has, the more bugs it can catch. Now, let me clear all this and run this again. Let me save. I apologize. This is to be implemented in the app.py function. All right, now let's run. As you can see, function is missing a type annotation is printed. Ignore these. Function is missing a type annotation is printed for this file. Alright, where is MyPy actually used? The answer is almost everywhere in modern Python development. FastAPI is heavily built around type hints. MyPy helps ensure request handlers and models are used correctly. Large backend applications rely on MyPy to maintain consistency between hundreds of modules. Many teams add MyPy to their automated checks in CI/CD pipelines. A pull request or PR cannot be merged unless MyPy passes successfully. When dozens or hundreds of developers work on the same system, static analysis becomes incredibly valuable. It catches mistakes long before they reach production. Now, let's summarize the biggest benefits. First, catch bugs earlier. Find an issue during development is far cheaper than fixing it in production. Second, safer refactoring. If you change a function signature, MyPy immediately identifies every broken call site. Third, better code quality. Type-checked code tends to be more predictable and easier to maintain. And finally, easier onboarding. New developers can understand the expected inputs and outputs of functions more quickly. These advantages become more important as projects grow larger. Now, let's quickly recap. Type hints describe what your code expects, but Python does not enforce them. MyPy reads those type hints and verifies that they are being used correctly. Because MyPy performs static analysis, it can detect many bugs before the program ever runs. For even stronger guarantees, we can enable MyPy strict, which performs a more comprehensive checks. In the next video, we'll explore advanced type hints. We'll learn about list, dictionaries, optional union, type dict, type aliases, etc. If you found this video useful, make sure to like the video, subscribe to the channel, and leave a comment telling me whether you've used MyPy before or not, and if you intend on using it now. Thanks for watching, and I'll see you in the next one. Hello everyone, and welcome back to the Python OOP series. This is the final video on this series. In the previous video, we learned about MyPy and how static type checking helps catch bugs before our code ever runs. We saw that type hints are more than just documentation. When combined with tools like MyPy, they become a powerful safety net for large Python projects. Today, we're taking one final step in our typing journey. We're going to learn about advanced type hints. These are typing features you will encounter in professional Python codebases, FastAPI applications, backend services, and large production systems. Today, we'll be covering typing collections, optional types, union types, type aliases, type dict, callable, type var, etc. By the end of this lesson, you'll understand the most important advanced typing tools used in modern Python development. So let's get started. Now, before we dive into advanced typing, let's do a quick recap of the previous video. We learned that type hints improve readability. They make code self-documenting and easier to understand. We also learned that MyPy can verify those type hints and catch mistakes before runtime. We also learned how to install MyPy using UV and pip. Today, we're building on that foundation and learning how to describe more complex data structures and functional relationships. Now, let's switch to code. Now, let's implement a list. So, as I said, one of the first limitations of basic type hints is containers. So, for our name list, we'll have three names: Alice, Bob, and say for C, Charlie. This tells us it's a list, but what kind of values are inside, or what kind of values are expected inside the list? It can be strings, integers, objects. Python does not know that. Now let's improve this. So what we can do is we can give square brackets here. We can give square brackets here, and str can be used. All right. Now we're being specific. This is a list containing strings. Let's look at a few more examples. Here, the scores dictionary expects string as key and integer as value. Here, user IDs, which is a set, expects only integers. And here, record is a tuple, which expects string and integer. These annotations tell both developers and tools exactly what each container should contain. This becomes extremely useful in larger applications where data structures are passed between many modules. Now, sometimes a value may not always exist. Let's imagine a user profile. Let me remove all this. Let me implement a get email function which shall either return string or a none type. All right. Now let's return none. This annotation tells us this function may return a string or a none. Now, in older Python versions, instead of this, let me comment this out. What was used was we used to import optional from typing. So from typing import optional. And what we used to do is we used to say, let's implement the same function again, get email. The pattern is almost exactly the same till here. Then we used to use the optional keyword and pass str or string, and then again we type return none or any other logic here. Both mean the same thing. However, this is used in today's systems more often, but you'll still come across these while reading older code. So let me comment this out and let me uncomment this one. All right. Now let's look at union types. Suppose an API accepts either an integer ID or a string ID. Say we are implementing a function called process user, which is a common function that is implemented in backend functions or backend applications. User ID can be either an integer or a string. Now, say process user returns an integer. Now we shall return int user underscore ID. All right. Now the function clearly communicates that multiple types, say integer and string, are acceptable. This is common in APIs, configuration systems, and data processing applications. Sometimes type definitions become long and difficult to read. Consider, now first let me remove all this. Now let's implement another get user function. And what we can do here is pass user ID, which is an int, and this shall return a dictionary of string, and either string or integer or say none. All right, now this is our function, and let's just pass. The return type here is technically correct. However, the problem is it's not very readable. Let's try and improve this. Instead of doing all this, what we can do is, let me not remove all the function. What we can do is we can create a dictionary called user ID. First, user ID is supposed to be an integer, then user profile, for example, which is to be returned, is a dictionary with the values required. For example, str, comma, str, or int, or none. All right. Now, instead of writing all this, what we can do is we can write user ID, and here we can put user ID and return user profile. This makes our code much easier to understand. Experienced engineers often use aliases to make complex types self-explanatory. One of the most useful typing features is typedict. Imagine we're working with API payloads. Without typedict, we might write something like this. Let me remove all this. Now we're entering typedict, so let me put typedict here. User and dictionary, and what we'll do is we'll open our dictionary with curly braces, and ID, say ID is 42, and username, say username is dev user, and an email, say email at the moment is none. There should be a comma here. All right. The problem is that the type checker does not know which keys should exist. Now let's make it explicit. Now from the same library where we imported optional, let's import something called typedict. And let's make a class called user payload, and we will be using typedict as its parent class. Now what we'll do here is we'll define everything. So int, similarly username is supposed to be str, and our final email, which can be either a string or none. Now let's create an object. Say user and user payload. we open curly braces, and what we can simply do is pass ID and 42, just like we did in the last one, and user name. So username can be the same div user. There should be invert. There should be these here, and comma again, and email shall be none. Typedict gives structure to dictionaries. This is extremely useful for API requests, API responses, configuration files, and database records. MyPy can now detect missing keys, incorrect types, and invalid structures automatically. Now let's briefly look at two advanced typing tools. Let me remove all this. Now the first tool we'll be looking at is called callable. Callable describes functions as values. So again, from typing, what we will be doing is importing callable, and let's apply an apply function, func, and callable, and open our braces, say a list of integers and a string. All right, now value is int. Now from this function, what we will be returning is a string, and what we will be returning is func value. This tells us the function parameter must accept an integer and return a string. Now let's look at type var, which is another one of these. So let me remove all of this and import type var. Now t is equals to, let me type t is equals to type var and say t. Now let's create a generic function. See, our function is called first, and what we will be sending is items list t, and this shall return t as well. Now what we will be doing is we will be returning items, say 0. Now let's test this. Now let's print first of say, let me open parentheses, say a comma b comma c. Now let's run this code. Let me open my terminal, new terminal, and as usual, for the last time in this series, let's type python main.py. We get a type var allows us to write reusable functions that remain type safe. So we are type safing the function regardless of the input type. This is the foundation of generic programming in Python. Now, where do these advanced type hints actually appear? The answer is everywhere. FastAPI uses type hints to generate API documentation automatically. Pydantic modules use type annotations to validate and serialize data. Teams working in large backend systems rely on advanced typing to improve maintainability and reduce bugs. As projects grow, advanced type hints help developers understand code faster and refactor with confidence. Typing has evolved from an optional feature to a standard practice in modern Python development. Now, this video marks the end of our Python OOP series. Let's look at how far we've come. We started with classes, objects, encapsulation. Then we moved into inheritance, polymorphism, and abstract-based classes. Then we explored Dunder methods, operator overloading, and the very important decorators. And finally, we explored generators, context managers, type hints, MyPy, and for the final video, advanced typing. Together, these topics form the foundation of professional Python development. Whether you're building backend systems, AI applications, automation tools, or web services, you will encounter these concepts regularly. Now, let's finish with a few key takeaways. Annotate your functions, annotate your classes, use meaningful types whenever possible, run MyPy regularly, and gradually adopt more advanced typing features as your projects grow. Type hints improve readability,
MyPy improve safety. Together, they help create cleaner and more maintainable software. Now, thank you for following this Python OOP series from beginning to the end. I don't imagine many of you are here. In the next series, we'll begin exploring PyTorch and modern machine learning development using many of the Python concepts you've learned throughout these lessons. I'll also be uploading system design videos or just in general Python and production grade backend system videos as we go. If you found this series helpful, please make sure to like the video, subscribe to the channel, and leave a comment. Tell me which topic was your favorite or what topic you'd like me to cover next. Thanks for watching, and I'll see you in the next one.